Welcome to the Sleepy Scientist, a place where you can let the day drift away as you settle in for the night. Tonight's journey takes us far beyond the familiar skies to a realm where entire galaxies wander through space and, every so often, gently collide in slow motion. Before we begin, may I ask, where are you listening from this evening? Whether you're curled up in bed, resting on the sofa, or gazing out at the night sky, I'm glad you're here. If you find these calming explorations helpful, a like and a subscribe would mean a lot. And for those already subscribed, thank you for being part of this quiet voyage through the universe. I'll do my best not to keep you awake, but if you happen to stay up a little longer, at least you'll leave with a few new wonders tucked into your mind. So, as your eyes grow heavy, let's begin our journey. After all, what really happens when galaxies collide? Collisions in space may sound dramatic, yet they unfold on timescales so vast and serene that they are less like car crashes and more like a slow, cosmic waltz. Galaxies, immense collections of stars, gas and dust, are not fixed in place. They move, pulled together by the invisible threads of gravity, drawn into graceful encounters that reshape them over billions of years. In this exploration, you'll discover how these celestial gatherings unfold, what becomes of the stars and planets caught in their embrace, and what role black holes and dark matter play in this grand choreography. We will also look ahead to the distant future, when our own Milky Way will meet its neighbour Andromeda, in a union written into the stars long before life appeared on Earth. These stories are not rushed. Like the galaxies themselves, we will drift slowly, pausing to notice the quiet beauty of each step along the way. Because within the great collisions of the universe lies a reminder that change, no matter how immense, can be both gentle and profoundly creative. If you could step back far enough, far beyond the reaches of our solar system, beyond the faintest glow of our neighbouring stars, you would begin to see that the universe is not scattered randomly, but arranged in vast glowing cities of stars. These are galaxies, immense structures bound together by gravity, each one containing hundreds of billions of suns, swirling gas, drifting dust, and an invisible substance called dark matter that outweighs everything we can see. Galaxies are not small embellishments on the canvas of the cosmos. They are the fundamental building blocks of the universe, the great archipelagos in an endless cosmic ocean. A galaxy is not a single entity so much as a community. Imagine a city viewed at night from far above. Each shining light is like a star, and together they form patterns of streets, districts, and neighbourhoods. A galaxy is very much the same, but on a scale that the human mind struggles to hold. The Milky Way, for example, is our home galaxy, a barred spiral system with somewhere between 200 and 400 billion stars. Many of those stars host their own planets, and around some of those planets, perhaps, life may stir. Yet even with all this complexity, the galaxy remains a single unit, circling around its centre like a grand wheel. What keeps these stellar metropolises together? Gravity. It is the quiet architect of the universe, the force that ensures stars do not simply drift apart into the void. Galaxies hold together because their combined mass bends the fabric of space, pulling stars, gas and dust into a coherent structure. However, the visible material we can see, the stars, the shining nebulae, the glowing clouds, is only part of the story. There is also dark matter, an unseen framework that makes up most of a galaxy's mass. We cannot see it directly, but without it, galaxies would not have the gravitational glue to remain intact. They would simply spin apart like a poorly tied bundle of fireworks. Galaxies come in different shapes and personalities, each sculpted by their history and environment. The most famous are spiral galaxies, graceful disks with long arms that curl outward like cosmic pinwheels. These arms are not solid structures but waves of density that encourage gas to collapse and form new stars, giving spirals their blue-white sparkle. Our own Milky Way belongs to this class, complete with a central bar of stars stretching across its core. When viewed from afar, spirals are breathtaking, grand whirls of light, as if the universe itself enjoyed doodling on the largest scale imaginable. Then there are elliptical galaxies. These are less ornate, often resembling smooth, glowing ellipsoids, without the distinct arms of a spiral. Their stars are older, their light more golden, and they typically contain less gas and dust for new star formation. Many of the largest galaxies in the universe are ellipticals, bloated giants that may have grown through the collision and merger of smaller systems. They are the stately elders of the galactic family, less flashy perhaps, but carrying the weight of history. The irregular galaxies, by contrast, define neat categories. They appear chaotic, often the result of gravitational encounters or turbulent pasts that disrupted any clear shape. Some are small, others surprisingly large, but they share one trait: unpredictability. Where spirals and ellipticals can be neatly catalogued, irregulars are the universe's rebels, a reminder that not everything in nature follows a tidy diagram. Astronomers have also noticed that galaxies can be grouped by size. There are the giants, containing trillions of stars, and then there are dwarf galaxies with only a few billion. Dwarfs are actually the most common type, like scattered cottages compared to the grand skyscrapers of spirals and ellipticals. Our own Milky Way is attended by several dwarf companions, such as the large and small Magellanic Clouds, which are visible from the southern hemisphere as misty patches of light. In time, these smaller galaxies will likely be absorbed into the Milky Way itself, illustrating that galaxies are not static but ever-changing participants in the cosmic drama. It's easy to picture galaxies as still, painted across the heavens like decorations. But in truth, they are dynamic. Stars orbit their galactic centres, clouds of gas drift and condense, and spiral arms shift like ripples across a pond. A galaxy is not a frozen snapshot, but a living system, evolving over billions of years. From the birth of new stars in bright nurseries to the quiet fade of ancient suns, galaxies contain the entire cycle of stellar life. They are vast libraries of cosmic history, with every star a page, every cluster a chapter. Despite this richness, galaxies are surprisingly delicate. The structures we see, spiral arms, bars, disks, exist only because of a careful balance between gravity, rotation, and mass. Disturb that balance, and the shape can be transformed. Collisions, interactions, and even the slow pull of neighbours can twist and reshape galaxies, leading to strange bridges of stars or elongated tails. In many ways, galaxies are both resilient and fragile, surviving for billions of years yet always susceptible to change. When astronomers first began to study the faint smudges in the night sky, there was great debate about what they were. Were these clouds within our own Milky Way, or were they island universes beyond? It was not until the early 20th century that Edwin Hubble provided clear evidence that these smudges were galaxies in their own right, far outside our own, each with its own stars and structures. Today, thanks to powerful telescopes, we know there are more galaxies in the observable universe than grains of sand on Earth beaches. That number stretches into the trillions, each one a city of stars, each one a story in the making. In this immensity, our Milky Way may seem ordinary, but in reality it is anything but. It is a spiral galaxy about 100,000 light-years across, spinning gracefully through space. At its centre lies a supermassive black hole, a hidden giant around which everything turns. From our vantage point, we see the galaxy as a pale band of light arcing across the night sky, a reminder that we live not just in a solar system, but as citizens of a much larger, grander community. Galaxies are, in a sense, the universe's neighbourhood associations, but with fewer arguments about lawn care, and more about who gets to consume the next passing dwarf companion. They are the social units of the cosmos, rarely isolated, often interacting, sometimes combining, and always shaped by their environment. Whether spiral, elliptical, or irregular, whether giant or dwarf, Every galaxy carries its own identity, its own rhythm, and its own place in the vastness of space. To understand galaxies is to understand the stage on which the universe plays out its grand story. They are both the backdrop and the main characters, silent and majestic, yet never static. And though the human eye sees only a handful on a clear night, telescopes reveal the truth. Galaxies are everywhere, stretching to the horizon of the universe, each one turning slowly in the darkness, each one a beacon of light against the infinite night. The universe may appear at first glance to be a place of stillness. Stars seem fixed in their constellations, the Milky Way arches steadily across the night sky, and galaxies look like silent smudges suspended in the void. Yet behind this calm facade lies constant motion. Galaxies drift, swirl, and sometimes collide, all under the influence of forces that are both familiar and mysterious. To understand why galaxies behave the way they do, it helps to meet the great shapers of the cosmos: gravity, the ever-present sculptor, and dark matter, the unseen hand guiding the dance. Gravity is perhaps the most famous of nature's forces, though it tends to get taken for granted. After all, it is the reason your feet stay on the ground, and why coffee cups have such a tragic tendency to smash when they slip from the table. Isaac Newton was the first to describe it in precise mathematical terms, showing that the same force that pulls an apple toward Earth also keeps the moon in orbit and the planets circling the sun. Later, Albert Einstein expanded the picture with his theory of general relativity, revealing that gravity is not so much a force pulling objects together as it is the bending of space and time itself. Massive objects curve the fabric of reality, and everything else follows those curves. On the scale of galaxies, gravity is the master artist. It gathers matter from the early universe into clumps, squeezes gas into stars, and shapes entire galaxies into spirals, ellipses, or irregular clouds. Without gravity, there would be no stars, no planets, no people wondering about stars and planets. It is the quiet director of the cosmic stage, invisible, but absolutely relentless. If the universe were a grand sculpture garden, gravity would be the sculptor's hand, patiently chiseling over billions of years. Yet gravity alone does not explain everything. When astronomers first began to study galaxies in detail, they noticed something puzzling. By looking at the way stars orbit within a galaxy, one can calculate how much mass must be present to keep them bound together. The problem was the visible matter, the stars and glowing gas, was not enough. Galaxies were spinning too fast to be held together by what could be seen. According to the math, they should have torn themselves apart long ago. Clearly, something was missing. That missing ingredient is what scientists now call dark matter. Despite the name, dark matter is not some sinister substance lurking in the shadows. It simply means matter that does not emit, absorb, or reflect light. In other words, it is invisible to our eyes and to most of our instruments, detectable only through its gravitational influence. Current estimates suggest that dark matter makes up roughly 85% of the matter in the universe, vastly outweighing all the stars, planets, gas clouds, and galaxies we can see. Think of a galaxy as a glowing lantern surrounded by an enormous invisible balloon. The lantern is the stars and dust, but the balloon is dark matter, holding everything in place. Without this unseen framework, galaxies would not exist as we know them. They would be unstable collections of stars, unable to maintain their beautiful shapes. Dark matter is the silent scaffolding of the universe, keeping the luminous structures we admire from flying apart. Although dark matter remains mysterious, we do know what it is not. It is not made of the familiar atoms that compose you, me, and the chair you're sitting on. It is not ordinary matter hidden in dark clouds or faint stars. Decades of observations have ruled out such possibilities. Instead, it appears to be something entirely different, some new kind of particle that does not interact with light. Scientists around the world are building sensitive detectors buried deep underground. hoping to catch the faintest whisper of dark matter passing through. So far, it remains elusive, but its fingerprints are everywhere in the heavens. Together, gravity and dark matter shape the grand architecture of the universe. They do not act in isolation. Rather, they cooperate to weave the cosmic web. Galaxies gather at the intersections of vast filaments of dark matter, forming clusters and superclusters. In between lie immense voids, regions nearly empty of galaxies. This large-scale structure of the universe looks remarkably like a three-dimensional spiderweb stretched across billions of light years. If you could step outside the universe and glance back, you would see threads of galaxies tracing the unseen scaffolding, laid down by dark matter and pulled tight by gravity. Now, why do galaxies move at all? After all, if gravity is binding them so carefully, shouldn't they remain in neat stationary arrangements? The answer is that galaxies are born with motion. In the early universe, tiny fluctuations in density gave some regions a slight advantage in pulling in matter. As these regions grew, their gravity attracted more material, which fell inward not in straight lines but along curved paths. This imparted spin and drift to galaxies as they formed. Even today, galaxies continue to move under the gravitational influence of their neighbours. The Milky Way, for example, is not floating idly in space. It is hurtling toward the Andromeda Galaxy at several 100,000 miles per hour. Fortunately, space is so vast that even at such speeds the collision will not happen for another 4 billion years. On the human scale, this feels like forever, but in cosmic terms it is just around the corner. The point is that galaxies are not isolated marbles. They are participants in a vast gravitational dance, each step influenced by every other partner. One of the most beautiful consequences of this motion is that galaxies often interact. Some merely brush past each other, distorting their shapes with tidal forces. Others embrace fully, merging into new forms. Gravity choreographs these encounters, pulling on the outskirts of galaxies long before their centres come close. Stars are shifted into long tails, gas clouds are squeezed into new star-forming regions, and central black holes may eventually spiral together. What seems like chaos is in fact the orderly unfolding of physical laws across incomprehensible distances. It is worth noting how patient gravity is. Human beings are used to thinking of collisions as violent, destructive events that happen in fractions of a second. On galactic scales, a collision is more like two clouds drifting together, a slow process lasting hundreds of millions of years. The forces at play are immense, but the pace is serene. Gravity works with a timescale so generous that even stars live and die, while galaxies gradually merge. Dark matter, too, plays a critical role in these cosmic interactions. When two galaxies collide, their visible matter may distort dramatically, but their dark matter halos interpenetrate like two invisible balloons brushing past one another. These halos are so much larger than the galaxies themselves that they help guide the outcome of the merger, shaping the final structure. Observing such events gives astronomers one of the best tools for mapping the otherwise invisible distribution of dark matter. In all of this, a profound truth emerges. The universe is not static. It is not a silent museum of frozen exhibits, but a living, shifting network of galaxies sculpted by forces both visible and hidden. Gravity bends the paths, dark matter holds the frames, and together they create the conditions for beauty on the grandest scales. To look at a galaxy, then, is to see the balance of power between what we know and what remains mysterious. It is to witness the patient artistry of the cosmos, a design carved not in stone, but in stars. Understanding these forces does not just explain why galaxies look the way they do, it also reveals why the universe is structured at all. Without gravity, matter would never have gathered into stars. Without dark matter, galaxies would never have held together long enough for those stars to form planets, and for life to emerge. Every breath, every thought, every dream owes its existence to these silent cosmic shapers. The universe is vast, but its story is written by surprisingly few characters, each with a role as old as time itself. Galaxies may look like fixed ornaments in the night sky, but they are anything but static. They are ancient travellers, evolving and reshaping themselves across spans of time so vast that even the life cycle of stars seems fleeting in comparison. To understand galaxies is to step outside the human sense of time altogether, and into a realm where billions of years unfold like chapters in a long, unhurried story. Every galaxy begins as a gathering of matter in the early universe. After the Big Bang, about 13.8 billion years ago, the cosmos was filled mostly with hydrogen and helium gas, spread almost evenly. Yet even in this near-uniform sea, there were tiny ripples, slight variations in density, so small they might seem meaningless at first. Over immense stretches of time, gravity amplified these ripples, pulling more matter into the slightly denser regions. What began as a faint imbalance eventually grew into the first clumps of stars and the earliest galaxies. These primitive galaxies were small, irregular, and often chaotic in shape. They contained only young, bright stars, since older generations had not yet existed long enough to age and fade. Gas was abundant, fueling vigorous bursts of star formation. Compared to the majestic spirals and massive ellipticals of today, these early galaxies were like seedlings just sprouting from the soil. They lacked symmetry, but they carried the potential for growth and change. As billions of years passed, galaxies evolved through both internal processes and external encounters. Internally, stars were born, lived out their lives, and died, enriching the surrounding gas with heavier elements like carbon, oxygen, and iron. These elements made it possible for planets to form around stars and eventually for life to emerge in at least one corner of the cosmos. Each generation of stars left its fingerprint on the galaxy's character, gradually shifting its light from a youthful blue to a more mature golden glow as younger stars became less common. Externally, galaxies were constantly shaped by interactions with their neighbours. In the crowded early universe, collisions were far more common than they are today. These encounters were not brief accidents, but long, drawn-out events, lasting hundreds of millions of years. When galaxies collided, their stars usually passed by one another without direct impact. After all, stars are tiny compared to the distances that separate them. Yet the overall structures of the galaxies change dramatically. Gas clouds crash together, triggering waves of starbirth. Spiral arms might be stretched into tidal tails, and two colliding galaxies might eventually merge into a single larger system. It is tempting to think of collisions as destructive, but in reality they are creative as well. Without them, galaxies would not have grown to the immense sizes we see today. The giant elliptical galaxies that dominate the centres of clusters are thought to be the products of many mergers over billions of years, a record of cosmic cannibalism written in starlight. Even the elegant spiral form of the Milky Way is not eternal. Its history includes smaller collisions that have left streams of stars arcing across the galactic halo, and its future almost certainly includes a grand union with Andromeda. This long life cycle of galaxies reveals how dynamic they truly are. A spiral galaxy may eventually lose its gas and slow its star formation, becoming redder and more quiescent. Over further billions of years, repeated mergers can smooth away the delicate spiral arms, leaving behind a more rounded elliptical form. By then, most of the galaxy's stars are old, glowing faintly as they exhaust the last of their nuclear fuel. The galaxy itself, though still vast and luminous, begins to quiet, a once bustling city gradually settling into a calm twilight. Timescales like these are almost beyond human imagination. To say that a collision between galaxies takes hundreds of millions of years is one thing. To truly grasp it is another. For perspective, the entire span of human civilization, from the earliest agricultural villages to the skyscrapers of today, covers only a few thousand years. Even the rise and fall of the dinosaurs occupied just a few 100 million years, a single chapter in a galaxy's life. Galaxies do not hurry. Their transformations unfold at a pace so measured that entire species and civilizations come and go without the galaxy noticeably changing at all. And yet within this vastness there is a strange comfort. To know that galaxies live for billions of years is to recognize that the universe is patient, that it allows time for cycles to unfold fully. Collisions, mergers, and the birth of new stars are not interruptions, but part of the natural rhythm. Galaxies are not fragile in the way a single star or a single planet might be. They are resilient collectives, capable of surviving encounters that would seem catastrophic on smaller scales. The Milky Way itself carries scars of its long life. Astronomers have traced streams of stars that were once part of smaller dwarf galaxies now absorbed into our own. These faint trails in the sky are reminders that galaxies live not in isolation, but in constant interaction. Each merger adds new chapters to a galaxy's history, subtly altering its shape, enriching its star population, and contributing to its slow but steady growth. Some galaxies live quieter lives than others, orbiting in relative solitude. Others inhabit crowded clusters, where encounters are inevitable and evolution is accelerated. The diversity of galaxy shapes we see today is in many ways a snapshot of their journeys through time. A graceful spiral may one day become a featureless ellipse. An irregular cloud may be tidied into a more coherent form. The universe is always at work, sculpting with gravity and chance. When reflecting on the long lives of galaxies, one cannot help but feel a shift in perspective. Human concerns, measured in hours, days, and years, seem fleeting compared to the slow drift of billions of stars across cosmic landscapes. Yet rather than diminishing the human experience, this contrast can be soothing. It reminds us that the universe is vast enough to hold all stories, from the brief flicker of a life to the grand arc of a galaxy. Each operates on its own timescale, neither more nor less important, but woven together into the tapestry of existence. To gaze at a galaxy, whether through a telescope or simply imagining its form, is to witness time stretched almost beyond comprehension. Its light has travelled across millions of years to reach us, carrying with it a record of ages long past, and the galaxy itself continues on, evolving in ways we can only glimpse across the brief span of our observation. Galaxies are not just collections of stars, they are chronicles of time, living monuments to the quiet patience of the cosmos. When we hear the phrase "galaxies colliding," the imagination leaps to chaos. One might picture stars crashing together like bumper cars, planets flying off into the void, or cosmic explosions ripping the heavens apart. It sounds like a scene from a science fiction blockbuster, fast, fiery, and catastrophic. But reality, as it so often does, paints a different picture. The science of galactic collisions reveals a process that is not so much an act of destruction, as it is a slow transformation, unfolding with a grace that belies the scale involved. The first and most important truth is that stars almost never collide directly, even when galaxies do. This might seem counterintuitive. After all, a galaxy contains hundreds of billions of stars, and when two galaxies overlap, shouldn't they smash into each other like cars on a crowded highway? The answer lies in scale. Stars, though immense compared to planets, are still minuscule compared to the distances that separate them. Imagine 2 grains of sand placed several miles apart. That is roughly the spacing of stars in a galaxy. Even when galaxies interpenetrate, the odds of 2 stars colliding head-on are vanishingly small. What actually happens is more subtle. The gravitational pull of each galaxy tugs on the other, distorting their shapes. This tidal interaction stretches them into long, elegant tails of stars, arcs that sweep across hundreds of thousands of light years. Gas clouds, much larger than individual stars, do collide and compress. It is here, in these interstellar clouds, that the real fireworks occur. Compressed gas collapses under gravity, triggering bursts of star formation. Collisions do not usually destroy stars. Instead, they create new ones, lighting up the galaxies in a fresh blaze of youthful brilliance. This starburst activity is one of the most spectacular outcomes of galactic collisions. When gas is compressed, it condenses into glowing nurseries of massive hot stars. These stars shine fiercely but live briefly, ending their lives in supernova explosions that enrich their surroundings with heavier elements. In this way, collisions contribute not just to the beauty of the universe, but to its chemical diversity. The carbon in your body, the oxygen you breathe, and the iron in your blood are all products of past generations of stars. Collisions accelerate that cycle, feeding the cosmos with new material for planets and life. Another key feature of galactic collisions is how they rearrange the motion of stars. Although stars rarely collide, their orbits can be altered by the shifting gravitational field. Some stars may be flung into long arcs around the new merged galaxy, while others settle closer to the centre. In some cases, entire solar systems could be gently displaced, moving from one part of a galaxy to another. From the perspective of a planet circling its star, the night sky would gradually change, constellations slowly unravelling as the galaxy reshaped itself. But to the inhabitants, if there were any, the process would be so slow they would never notice across a single lifetime. One of the enduring myths about galaxy collisions is that they are violent, explosive events that obliterate everything in their path. The truth is far calmer. Galaxies pass through one another like phantoms, their stars mostly untouched, their gas clouds igniting new life rather than ending it. It is a reminder that even words like collision can be misleading when applied to the vastness of space. These encounters are not crashes, they are mergers, dances, and gradual transformations. When two galaxies of similar size merge, the end result is often a new type of galaxy altogether. Spiral arms can be torn apart, leaving behind a more rounded, elliptical shape. Over billions of years, the chaotic aftermath settles into a quieter structure, with old stars drifting serenely in their new orbits. The galaxy may appear smoother, less ornate than a spiral, but it carries within it the memory of its past unions. In this sense, every elliptical galaxy is a kind of monument to ancient collisions, the cosmic equivalent of a scar that has healed into a new form. Sometimes the merging galaxies are unequal in size, with a giant absorbing a smaller companion. Astronomers call this galactic cannibalism, though it is less gruesome than it sounds. The smaller galaxy is gradually stretched apart, its stars and gas assimilated into the larger one. Evidence of this process can be seen in the faint streams of stars that surround many galaxies, remnants of dwarfs that have long since been swallowed. Even our own Milky Way is in the process of consuming smaller neighbours, their remnants orbiting as ghostly trails across the sky. Gas dynamics play an especially important role in these cosmic encounters. Unlike stars, gas clouds are large enough to collide directly. When they do, shock waves ripple through them, causing the gas to lose energy and sink toward the galactic centre. This can feed supermassive black holes lurking at the heart of galaxies, causing them to flare into active galactic nuclei. These brilliant beacons, sometimes brighter than the entire galaxy itself, are powered by matter spiralling into the black hole at near-light speeds. In this way, collisions can awaken dormant black holes, turning quiet galaxies into quasars visible across the universe. From the human perspective, the pace of all this is unimaginable. A galactic collision does not happen overnight. The initial approach may take hundreds of millions of years, followed by a drawn-out dance of close passes, separations, and reapproaches. Only after perhaps 1 billion years do the galaxies finally coalesce into a single structure. To put that in perspective, 1 billion years is roughly the time it took for simple life on Earth to evolve into complex multicellular organisms. While galaxies slowly weave themselves together, entire worlds can rise, flourish, and fade without ever witnessing the full event. For astronomers, the study of galactic collisions is both a window into the past and a forecast for the future. By observing galaxies in various stages of merging, they can reconstruct the life cycle of these grand encounters. The Antennae galaxies, for example, are two spirals currently in the throes of collision. their long tidal tails arcing outward like insect feelers. The Whirlpool Galaxy shows evidence of a smaller companion disturbing its structure, tugging on its spiral arms. Each of these cosmic examples is a snapshot of an ongoing story, a frozen frame in a film that plays out over eons. In understanding these collisions, we also come to appreciate the role of patience in the universe. To human eyes, they might seem catastrophic, but on cosmic timescales they are neither sudden nor ruinous. Instead, they are natural steps in the evolution of galaxies, essential for growth, renewal, and change. If galaxies could speak, perhaps they would not describe these encounters as disasters, but as transformations, opportunities to become something new. In the end, the science of galactic collisions reminds us that appearances can be deceiving. What seems like destruction is often creation in disguise. The stars carry on undisturbed, the gas ignites with fresh energy, and new galaxies emerge from the union. Rather than imagining fiery wrecks in space, it is better to picture a slow dance, a blending of structures guided by gravity and lit by the birth of countless new suns. It is a vision not of violence, but of cosmic renewal, written across billions of years in the light of the stars. When two galaxies meet, the result is not simply a rearrangement of stars and gas, but a display of cosmic artistry. These encounters create structures so striking that even seasoned astronomers are left in awe. Long tails of starlight unfurl into the darkness, bridges of matter stretch between galaxies like glowing handshakes, and delicate streams arc across space in patterns that resemble brushstrokes on a canvas far larger than any human imagination. This is why galactic collisions are often described as ballets. They're graceful, deliberate, and hauntingly beautiful. One of the most captivating features of these encounters are tidal tails. These are elongated streams of stars and gas that extend outward from colliding galaxies, sometimes stretching for hundreds of thousands of light years. They form when the immense gravitational pull of one galaxy distorts the structure of another, tugging on its outskirts and flinging material outward in elegant arcs. To an observer, tidal tails look like ribbons of light drifting into the void, their curves echoing the flow of gravity itself. Some tails eventually curl back, falling into the merged galaxy, while others remain as faint reminders of past interactions, lingering for billions of years. Bridges are another common feature of galactic interactions. These glowing connections form when material is drawn from one galaxy to another, creating a luminous thread between them. To the eye, these bridges resemble trails of starlight linking two islands in the dark ocean of space. They are the visible evidence of gravitational attraction at work, a cosmic tug-of-war rendered in stars and gas. Over time, such bridges may collapse back into their galaxies, but for the duration of their existence they give the impression of galaxies reaching out, almost touching. Streams of stars can also result from collisions, formed when galaxies tear smaller companions apart. These streams, often faint but remarkably long, wrap around galaxies like halos or form graceful loops in the night sky. In our own Milky Way, such streams have been detected as remnants of dwarf galaxies consumed long ago. They act as the lingering choreography of past dances, subtle yet elegant signatures of encounters that shape the galaxy we live in today. The sheer beauty of these structures is amplified when seen through telescopes that capture both visible and invisible light. Observations in ultraviolet reveal bursts of new stars forming within tidal tails, while infrared views show glowing dust heated by stellar nurseries. Radio telescopes pick up hydrogen gas stretched across vast distances, mapping the invisible currents that feed star formation. Taken together, these perspectives reveal collisions not as chaotic events but as ordered compositions, each wavelength of light adding another note to the cosmic symphony. While direct observation shows us galaxies mid-performance, computer simulations allow us to replay their entire choreography. With the help of modern computing power, astronomers can model galaxies as collections of millions of particles, each representing stars, gas, or dark matter. When two simulated galaxies are set on a collision course, the resulting images are astonishingly close to reality. Spirals twist, tails unfurl, and bridges appear in just the way they do in actual observations. These simulations are not only scientifically valuable, but artistically mesmerizing, offering a chance to watch billions of years unfold in just a few seconds. What makes these simulations especially striking is how they reveal the underlying rhythm of the universe. The galaxies sway and stretch, not with violence, but with a grace dictated by gravity's laws. They approach, overlap, recoil, and return, much like dancers performing a duet. Eventually, they merge into a single form, the chaos giving way to calm once more. The pace is slow, yet the patterns are intricate, showing how simple forces can produce complexity and beauty on scales that defy comprehension. For those who view these collisions, whether through telescopes or simulations, the imagery often evokes comparisons with earthly art forms. The arcs of tidal tails resemble brushstrokes from an unseen hand. The looping star streams mimic calligraphy written across the sky. The delicate curves of bridges could be mistaken for the flowing lines of a ballet dancer mid-motion. There is no intention behind these cosmic displays, no audience they were created for, yet they stir in us the same response that great art does, a quiet sense of wonder. The calm pace of these galactic dances is another part of their beauty. Unlike the frantic violence we might expect from the word collision, galaxies move with an unhurried grace. Their encounters last hundreds of millions of years, each step in the dance stretched across spans longer than all of human history. To an observer watching from afar, the spectacle is serene rather than frantic. Even in their most dramatic moments, galaxies move with a patience that reflects the deep time of the cosmos. Consider the antennae galaxies, one of the most famous examples of a galactic collision. From Earth, they appear as two spirals locked in embrace, their cores glowing brightly while long tails of stars extend outward like curved antennae. Within these tails, young stars sparkle in clusters, born from the compression of gas. The entire system is alive with energy, yet the arrangement is elegant, not chaotic. The antennae remind us that even in upheaval, the universe produces forms that captivate the eye. Another striking case is the Cartwheel Galaxy, whose unusual ring shape was created when a smaller galaxy passed directly through a larger disk. The impact sent ripples through the stars and gas. Much like a stone thrown into water creates concentric circles. These ripples triggered waves of star formation, producing a glowing outer ring that gives the galaxy its name. From a scientific perspective, the cartwheel is an example of how collisions can reorganize matter on a colossal scale. From an artistic perspective, it looks almost too perfect, like a deliberate design etched against the dark. What makes these displays all the more remarkable is their impermanence. Tidal tails eventually fade, bridges collapse, and streams of stars disperse into halos. The beautiful forms we admire are fleeting chapters in the lives of galaxies, visible only for a few 100 million years before they are reabsorbed. In cosmic terms, this is brief, a passing flourish in a performance that stretches across eternity. The fact that we are here to witness them at all feels like a small gift, a reminder that beauty can emerge at any scale, even if only for a while. Perhaps the most calming way to imagine these collisions is as a cosmic dance floor, where galaxies glide past one another in endless waltzes. There are no sudden movements, no rushed steps, only the steady pull of gravity guiding their motions. Each galaxy bends and sways, trailing ribbons of light that sweep through the darkness. From a distance, the sight is tranquil, almost meditative. It is the kind of performance that could lull the mind into peace, as if the universe itself were choreographing a lullaby. The galactic ballet is a testament to the power of perspective. From up close, a collision involves turbulence, shocks, and starbursts. But from afar, the grand arcs and sweeping curves reveal order and grace. It shows how the same event can be seen as both disruptive and beautiful, depending on the scale at which it is viewed. And in that duality lies much of the fascination. Collisions remind us that the universe is not just a place of cold mechanics, but also a place where physics writes poetry in the stars. Across the cosmos, countless galaxies have collided, merged, and reshaped themselves. But a few have become true icons of these encounters. They are the showpieces of astronomy, the galactic celebrity couples that draw attention whenever their portraits are released. Some are caught mid-embrace, others in the aftermath of dramatic encounters, and each tells a story of how gravity sculpts the universe. If Galaxies had tabloids, these would be the cover stars, with messy breakups, glowing makeovers, and dramatic new identities on display for all to see. One of the most famous examples is the antennae Galaxies, located about 45 million light-years away in the constellation Corvus. At first glance, they resemble two spirals caught in the act of crashing together. Their bright overlapping centres shine with starburst activity, while two enormous tidal tails stretch outward like long antennae, giving them their name. These tails are not just pretty flourishes, they are evidence of stars and gas being pulled into vast arcs by the tug of gravity. In these elongated streams, astronomers have discovered clusters of newly formed stars, glowing with youthful blue light. It is as if the collision has sparked fireworks that continue to blaze across hundreds of millions of years. The antennae are a perfect laboratory for studying what happens when galaxies merge. Observations in multiple wavelengths, visible, infrared, ultraviolet and radio, reveal a system brimming with activity. Dense pockets of gas are collapsing into stars at astonishing rates, creating regions packed with young clusters. At the same time, older stars are being redistributed, flung into new orbits that will eventually settle into a calmer shape. In a few billion years, the antennae will no longer look like two spirals at all, but will have relaxed into a single, larger elliptical galaxy. What makes them remarkable is not only their beauty, but their timing. They are caught at just the right stage of collision for us to witness both the chaos and the creation, the disorder and the order simultaneously. Another icon of galactic interaction is the Whirlpool Galaxy, also known as Messier 51. Situated about 23 million light-years away, it is a stunning face-on spiral that looks almost too perfect to be real. Its graceful arms wind outward in flawless symmetry, glowing with the light of billions of stars. But what truly makes the Whirlpool a star of the cosmic stage is its ongoing interaction with a smaller companion galaxy, NGC 5195. This dwarf galaxy is visibly tugging on the Whirlpool's spiral arms, distorting them and triggering bursts of star formation. The sight of the Whirlpool and its companion is one of the most photogenic in all of astronomy. Images from the Hubble Space Telescope reveal dust lanes curving across its arms like delicate brushstrokes. Glowing pink regions mark places where massive stars are forming, while clusters of blue stars highlight areas of recent stellar birth. The smaller galaxy, despite being much less luminous, exerts a powerful influence, dragging material outward and giving the Whirlpool its slightly exaggerated arms. If the Whirlpool Galaxy were a celebrity, its companion would be the mischievous partner responsible for both drama and glamour, reshaping its appearance for the cosmic cameras. The Whirlpool is a reminder that collisions and interactions need not always be catastrophic to be dramatic. Even a smaller galaxy can stir up spectacular changes in a much larger one. In this case, the encounter has enhanced the Whirlpool's beauty rather than diminished it, giving it the elegant arms that have made it one of the most studied spirals in the sky. Over time, however, the relationship will deepen. The smaller companion will eventually merge fully with the Whirlpool, leaving behind a different structure. For now, though, we get to enjoy the show at its most dazzling stage. If the antennae are the explosive rock stars of galactic collisions and the Whirlpool is the glamorous movie star, then the Cartwheel Galaxy might be considered the avant-garde artist. Roughly 500 million light-years away in the constellation Sculptor, it is one of the most unusual galaxies ever observed. Its appearance is unlike that of any ordinary spiral or ellipse. Instead, it resembles a glowing wheel, with a bright ring of stars surrounding a central hub. Radiating spokes connect the ring to the core, completing the illusion of a cartwheel rolling silently through space. The cartwheel's shape was not born from symmetry alone, but from a dramatic encounter. Astronomers believe a smaller galaxy passed directly through its disk, creating ripples that spread outward through the stars and gas. These ripples acted much like the waves on a pond after a stone is thrown in, compressing gas as they moved and igniting waves of star formation. The bright outer ring is the leading edge of this ripple, glowing with clusters of newly born stars. It is a striking example of how collisions can reorganize matter into patterns that are both scientifically fascinating and visually extraordinary. Studying the Cartwheel Galaxy provides valuable insights into the physics of galactic interactions. The waves of star formation triggered by the collision reveal how shock fronts move through gas on enormous scales. The galaxy is also a reminder of how creative these events can be, producing forms that no one could have predicted from simple theory alone. When first discovered, the cartwheel puzzled astronomers precisely because it looked so different from anything else in the sky. Now it stands as a cosmic masterpiece, one of those rare galaxies that refuses to fit neatly into categories. What unites these three galaxies, the antennae, the whirlpool and the cartwheel, is not just their fame but their individuality. Each highlights a different stage or aspect of galactic collisions. The antennae show us the chaotic middle act, where tails unfurl and starbursts ignite. The whirlpool captures a more subtle tug-of-war, with a companion reshaping a spiral into elegance. The cartwheel demonstrates the creativity of cosmic encounters, where a single pass-through can transform an ordinary disk into something entirely unique. Together, they illustrate the diversity of outcomes that gravity can produce when galaxies cross paths. There are, of course, countless other examples scattered across the universe, yet these particular galaxies have captured human imagination because they combine scientific importance with visual spectacle. They are the galaxies that appear on posters, in textbooks, and as screensavers on laptops. They are the celebrities of the galactic world, admired not just for what they teach us but for how they look. And like all celebrity couples, their stories come with drama, messy entanglements, long separations, and inevitable transformations. It is worth remembering, though, that what we see is only a snapshot. The antennae will one day merge into a calmer form. The whirlpool will eventually absorb its companion. The cartwheel's glowing ring will fade as the ripple subsides and its stars age. The beauty we admire today is temporary, frozen in time for a few 100 million years before it changes into something else. But in cosmic terms, that is more than enough time for us to pause, look, and marvel. When astronomers study these galaxies, they are not just documenting curiosities, they are piecing together the history of galactic evolution itself. Each interaction is a clue to how galaxies grow, how stars are formed, and how structures larger than imagination emerge from simple gravitational laws. The antennae, the whirlpool, and the cartwheel are not isolated spectacles. They are chapters in the ongoing story of the universe. Yet they remain more than data points. They are reminders that the cosmos is not only vast and complex, but also profoundly beautiful. If galaxies truly are the celebrity couples of the universe, then these three are on the front page for good reason. Their stories are dramatic, their appearances unforgettable, and their legacies enduring. They show us that even on scales of billions of years and trillions of stars, there is still room for elegance, artistry, and wonder. In the grandest ballroom imaginable, they are the dancers who caught the spotlight, twirling gracefully as the universe looks on. At the heart of nearly every large galaxy lies something extraordinary and mysterious, a supermassive black hole. These giants can weigh millions, even billions, of times more than the Sun, yet they occupy a region of space smaller than our solar system. Invisible on their own, they reveal their presence through the way they affect their surroundings. Stars whipping around at tremendous speeds, gas clouds heating as they spiral inward, and sometimes entire galaxies lit up by the radiation of matter falling into their depths. Though galaxies are vast collections of stars, gas, and dark matter, their centres are often ruled by these compact titans, like gravitational anchors holding the whole system together. The connection between galaxies and their central black holes is profound. Observations have shown that the mass of a supermassive black hole is linked to the mass of the galaxy's central bulge of stars. The bigger the bulge, the bigger the black hole. This suggests a kind of cosmic partnership. Galaxies and black holes grow together, feeding one another across billions of years. When galaxies collide, this relationship is put to the test in some of the most dramatic ways imaginable. Imagine two galaxies on a collision course, each carrying a supermassive black hole at its centre. As the galaxies draw closer, their stars and gas swirl into new orbits, and gravitational tides stretch their shapes. Over millions of years, the galaxies overlap, their centres inching nearer and nearer. Eventually, the two black holes are brought into the same neighbourhood. At first, they orbit one another at great distances, circling slowly within the merged galaxy. Gradually, though, they spiral closer, losing energy with each orbit. What began as two separate centres of gravity becomes a binary black hole system. Two colossal objects locked in a slow, inescapable embrace. This dance can last for millions of years, but it does not last forever. As the black holes orbit each other, they disturb the very fabric of space and time, sending out ripples known as gravitational waves. These waves carry energy away from the system, causing the orbit to shrink ever so slightly. The closer the black holes get, the faster they orbit, and the stronger the waves they emit. In the final stages, the two black holes whirl around each other at nearly the speed of light before merging into a single, even larger black hole. The event is so powerful that for a brief instant it releases more energy than all the stars in the visible universe combined, though most of that energy travels not as light but as gravitational waves. Gravitational waves are one of the most astonishing predictions of Einstein's general theory of relativity. In simple terms, they are ripples in space and time itself, spreading outward like waves on a pond after a stone is dropped in. If you could somehow see them, space would appear to stretch and squeeze as the waves pass through. On Earth, we are constantly being washed by faint gravitational waves from distant cosmic events, though they're so weak that they go unnoticed in everyday life. Detecting them requires instruments of unimaginable precision, capable of measuring distances smaller than the width of a proton. In 2015, scientists achieved this feat for the first time. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, recorded the faint signature of two black holes merging over 1 billion light-years away. The signal lasted only a fraction of a second, but it confirmed the existence of gravitational waves beyond doubt. It also proved that black holes, once thought of as purely theoretical, not only exist, but collide and merge as part of the natural order of the cosmos. Since then, dozens of gravitational wave detections have been made, each one a whisper from the deep universe, telling the story of massive objects colliding. When galaxies merge, their central black holes eventually follow suit, though the timescales are long. First, they must sink toward the merged centre, slowed by the gravitational tug of surrounding stars and gas. Then they form a binary, orbiting one another until gravitational waves carry away their remaining energy. For astronomers, these processes are both a challenge and an opportunity. The challenge lies in observing them directly, since even the brightest signatures are faint compared to the scale of the universe. The opportunity is that gravitational waves open a new way of seeing, allowing us to listen to the cosmos rather than just looking at it. The merger of supermassive black holes is expected to create some of the most powerful gravitational wave signals of all. Future observatories, such as the planned space-based detector called LISA, the Laser Interferometer Space Antenna, are being designed to pick up these low-frequency waves. Unlike ground-based detectors that capture the quick chirps of smaller black hole mergers, LISA will be able to track the slow, deep rumble of supermassive giants spiraling together for months or years. These detections will provide new insights into how galaxies grow, how black holes feed, and how gravity itself behaves under extreme conditions. What makes the role of black holes in galactic collisions so fascinating is the duality of their nature. On the one hand, they are destructive, devouring anything that comes too close. On the other, they're creative, shaping galaxies, driving star formation, and producing phenomena that light up the cosmos. When two supermassive black holes merge, they do not simply erase what was there before. They create a new centre of gravity, a fresh anchor for the merged galaxy, and send ripples across the universe that can be detected billions of years later. The thought of two black holes merging may sound terrifying, but it's important to remember the scale involved. Even if the Milky Way and Andromeda galaxies collide in the distant future, their central black holes will not pose a danger to Earth. By the time the galaxy's centres finally meet and the black holes merge, our Sun will likely have long since exhausted its fuel, and Earth may no longer exist as a habitable world. The event will be spectacular on the cosmic stage, but far removed from the concerns of life as we know it. The role of black holes in collisions highlights the extraordinary patience of the universe. These processes unfold not in years or centuries, but in millions and billions of years. The orbits tighten, the waves ripple outward, and eventually, in a climactic moment, two invisible titans become one. It is a story both serene and dramatic, a reminder that even the darkest objects in the universe are part of its beauty. To imagine it in more gentle terms, think of two dancers circling one another, drawing closer with each turn. The floor beneath them hums softly with the vibrations of their steps, until finally they meet in a single, graceful movement. That is what galaxies carry in their centres, not just stars and dust, but hidden performers whose steps send ripples across the very fabric of reality. And while we may never witness such an event directly with our eyes, our instruments now allow us to feel the music of their dance, echoing faintly across the cosmic sea. When galaxies collide, the images we see through telescopes suggest chaos, long tails of starlight, distorted spirals, and great glowing arcs of gas. Yet if you shift the focus away from the grand view and instead look at the experience of an individual star, the story changes. For most stars, a galactic collision is not the violent upheaval one might expect. Instead, it is more like a slow drift, a gentle reshuffling of their place in the cosmic city, a process so gradual that even the longest-lived creatures on Earth would never notice it happening. To understand this, it helps to remember the scale of space within a galaxy. Stars are separated by such immense distances that even when galaxies interpenetrate, the odds of any two stars colliding are so tiny they might as well be zero. If the Sun were reduced to the size of a marble, the nearest star, Proxima Centauri, would be another marble placed several hundred kilometers away. That is the level of emptiness we are dealing with. Galaxies may look dense when seen from a distance, but in truth they are mostly void. This means that for a star, a galactic collision is not like a car crash, but more like being a single grain of sand in two sandstorms passing through each other. Close, but rarely touching. What does happen is a change in motion. A star orbits the centre of its galaxy, held in place by the combined gravity of everything else. When another galaxy comes close, the gravitational field shifts. Stars are pulled into slightly new orbits, some stretched outward into long tails, others nudged inward toward the galactic core. These changes happen slowly, over millions of years. A star that once traced a perfect circle might find itself on a longer ellipse, or perhaps drifting toward a new region of the galaxy. To the star itself, nothing feels different. It simply continues on its path, following the gravitational script written for it by the larger structures around it. For stars like the Sun, with planets in orbit, the story remains surprisingly calm. The star's gravitational grip on its planets is much stronger than the subtle pull of distant galaxies. Earth, for example, orbits the Sun at a distance of 93 million miles, and the Sun's influence at that range dwarfs any tidal effects from faraway stars. This means that when galaxies collide, solar systems are usually preserved intact. Planets continue to circle their stars, seasons pass, and life, if it exists, may carry on without ever realizing that the entire galaxy is being reshaped. Of course, there are rare exceptions. If a star passes very close to another star during the interaction, their gravitational fields can tug on one another, potentially disrupting or even ejecting planets from their orbits. A planet might be flung into interstellar space, becoming a lonely rogue world adrift without a parent star. But such close encounters are vanishingly rare, and for the overwhelming majority of solar systems, galactic collisions are quiet, almost unnoticeable affairs. In some cases, stars are pulled into great arcs that extend far beyond the galaxy's centre, forming tidal tails visible across vast distances. For those stars, the collision alters their place in the universe more dramatically. A star that once lived in the bustling suburbs of its galaxy may find itself hurled into the thinly populated halo, circling the outskirts for billions of years. Yet even then, the star itself does not break or shatter. It continues to shine as it always has, its nuclear furnace deep within, largely indifferent to the slow ballet of galaxies around it. The endurance of stars in these cosmic dances is a humbling reminder of scale. Stars live for millions, sometimes billions of years. The Sun, for instance, is about halfway through its 10 billion year lifespan. During that time, galaxies may collide, merge, and change shape entirely, but the Sun's steady glow will continue largely unaffected. From the star's perspective, the galaxy is less a stable home than a shifting backdrop, a stage whose scenery changes while the performance itself carries on undisturbed. It is also important to note that galactic collisions can lead to the birth of new stars. When gas clouds within colliding galaxies crash together, they ignite bursts of star formation. These newborn stars often gather in clusters, burning with fierce blue light and living fast, dramatic lives. For them, a collision is not simply a rearrangement, but the very reason they exist. They would never have formed without the squeeze of gas triggered by the galaxy's embrace. So while older stars endure quietly, younger stars come into being because of the turbulence, adding fresh light to the universe. From the imagined perspective of a star, there is serenity in all of this. Whether it drifts slightly outward, is tugged into a new orbit, or remains near its original neighbourhood, its fundamental existence is unchanged. The fusion reactions at its core continue, layer after layer of hydrogen converting to helium, releasing energy that shines across space. It may be nudged, tilted, or stretched into a new path, but the star itself is steady, a lighthouse shining through the cosmic storm. Even when supermassive black holes merge at the centres of colliding galaxies, stars far from the core barely notice. Their lives continue unaffected, too distant from the central upheaval to be disturbed. The universe is large enough and galaxies are spacious enough that the fireworks of collisions often leave most stars untouched. It is a paradox. The most spectacular events we can see across the cosmos are, for most of the stars involved, quiet affairs like background music playing while they carry on with their own routines. This calm endurance of stars is perhaps the most poetic lesson of galactic collisions. Human lives are measured in days, years, and decades, fragile and fleeting. Stars, by contrast, measure their lives in eons. They persist through upheaval, shining steadily while galaxies twist and reshape themselves. To think of a star's perspective is to think of patience on a scale almost unimaginable. Change comes, but it comes so slowly that the star itself hardly notices, continuing to burn with the same quiet light. It is comforting in a way to imagine our sun in the distant future, carried along in the great merger between the Milky Way and Andromeda. While the galaxies around it stretch into new forms and their centres spiral together, the sun will go on shining, perhaps with Earth still circling, perhaps not, but still producing the light that nourishes its little corner of space. From the star's perspective, there will be no chaos, only continuity. In the end, the stars remind us that beauty in the universe does not always come from dramatic upheaval. Sometimes it comes from constancy, from the ability to endure while everything else changes. Galaxies may collide and merge, their shapes transforming into something new, but the stars carry on, steady beacons in a shifting universe. Their perspective is one of quiet resilience, a lesson written not in words but in light that has shone across billions of years. When two galaxies collide, the first thing that captures the eye is their altered shapes. Spirals stretched into ribbons, streams of stars arcing into space, and luminous bridges connecting one to the other. Yet perhaps the most important transformations happen not in the stars that already exist, but in the clouds of gas and dust that drift between them. These vast reservoirs, invisible to the naked eye but glowing in radio and infrared light, are the raw material of new suns. When galaxies meet, these clouds are shaken, compressed and stirred into action, setting off cascades of star formation that light up the cosmos in brilliant displays. Gas and dust may sound unimpressive at first. Dust conjures images of the neglected top of a bookshelf, and gas suggests something equally mundane. But on cosmic scales, these substances are anything but ordinary. Interstellar gas, made primarily of hydrogen, fills galaxies like a thin mist, while dust grains, tiny specks of heavier elements such as carbon and silicon, scatter light and shape the appearance of nebulae. Together, they form the fertile soil from which stars and planets emerge. Without gas and dust, galaxies would be lifeless collections of aging suns. With them, they are nurseries, capable of birthing new generations of stars. A galactic collision is like a gardener turning the soil. Gas clouds that were drifting lazily are suddenly compressed by gravitational forces and by direct impacts with other clouds. When compressed, their internal pressure rises, and gravity can more easily overcome resistance, causing the clouds to collapse. Within these collapsing regions, knots of matter condense into protostars, each one igniting nuclear fusion once it becomes dense and hot enough. From what appears, on the surface, to be an act of disruption, new light emerges. Astronomers call these intense periods of star formation starbursts. During a starburst, a galaxy can produce stars at rates tens or even hundreds of times higher than usual. Some galaxies, quiet for billions of years, suddenly become ablaze with new clusters of massive bright stars. These stars burn hot and blue, radiating tremendous energy but living short lives, often only a few million years before exploding as supernovae. In their brief but brilliant existence, they reshape their environment, heating surrounding gas and seeding it with heavy elements that will one day become part of future stars, planets, and perhaps even living creatures. Starbursts are not just dramatic, they are transformative. They can change the appearance of a galaxy entirely, filling it with glowing regions that shine in pink and red as hydrogen gas is ionized by ultraviolet light from young stars. Images of colliding galaxies like the antennae reveal dozens of such regions, like jewels scattered across their distorted forms. Each glowing patch is a cluster of stars being born, a reminder that even in upheaval, creation thrives. Nebulae play a starring role in this process. These are the colourful clouds we often see in astronomy photographs, such as the famous Orion Nebula. In colliding galaxies, nebulae are shaped and energized by the tidal forces at work. Shock waves from colliding gas clouds ripple through them, compressing their filaments and igniting bursts of formation. Seen through telescopes, these nebulae glow in vivid hues, each colour corresponding to different elements: red from hydrogen, green from oxygen, blue from helium. They are like cosmic gardens in full bloom, nurtured by the very collisions that at first seem so destructive. The poetic image of galaxies as gardeners is apt. They scatter seeds of starlight into new places, cultivate fresh clusters, and replenish the universe with energy and matter. Old stars die, their remains enriching the interstellar medium with heavier elements. Collisions then stir that medium into new shapes, ensuring the cycle of birth continues. It is a process of recycling on the grandest possible scale, one in which destruction and creation are inseparably intertwined. The scale of this starbirth is staggering. A single massive star-forming region triggered by a collision can contain thousands of new suns. Some will be like the sun, steady and long-lived. Others will be giants, burning brightly and briefly before collapsing into neutron stars or black holes. A few may even host planetary systems capable of developing conditions for life. To think that galactic collisions, events spanning hundreds of millions of years, can lay the groundwork for future worlds adds another layer of wonder to their story. The physics behind this is intricate but elegant. As two galaxies interact, their mutual gravity pulls on gas clouds, funneling material toward their centers. This inflow can feed the central black holes, igniting quasars, but it also increases the density of the central regions, where star formation flourishes. At the same time, gas clouds in the outer regions may be drawn together, sparking starbirth in unexpected places. The result is a galaxy dotted with regions of activity, a patchwork quilt of glowing clusters stitched by the hand of gravity. Yet starbursts cannot last forever. The very process of intense star formation consumes gas rapidly. Within a few 100 million years, the fuel runs low, and the burst fades. What remains is a galaxy transformed, often redder, quieter, and dominated by older stars. In this way, collisions not only create but also accelerate the evolution of galaxies, pushing them through phases of activity and into more settled forms. The gardens bloom, the harvest is gathered, and then the soil rests until the next stirring begins. For astronomers, watching these starbursts is like catching the universe mid-sentence. They are rare in cosmic terms, since galaxies spend far more of their lives in quieter phases. To see a galaxy in the throes of a starburst is to glimpse a moment of vitality, a burst of youth and energy in an otherwise measured existence. It is a reminder that galaxies, though ancient, still have the capacity for sudden renewal, sparked by the chance encounters of gravity. In reflecting on these processes, there is something soothing about the balance they reveal. The universe does not waste. Gas and dust that might otherwise drift indefinitely are gathered into stars. Elements forged in stellar hearts are spread by supernovae, only to be reincorporated into new suns and planets. Collisions, though they appear catastrophic from afar, are part of this grand recycling program. They are the gardeners of the cosmos, turning the soil, planting seeds, and nurturing light where once there was darkness. Even from Earth, separated by millions of light years, we can appreciate this beauty. Telescopes allow us to see glowing arcs of starbirth, colours painted by young stars against the black canvas of space. Every such image is both a scientific record and a work of art, proof that creation thrives even in upheaval. The universe is not only vast but fertile, always finding ways to bring forth new light. And so, in the quiet glow of starbursts and nebulae, we glimpse the truth of galactic collisions. They are not only endings but beginnings, not only disruptions but acts of cultivation. They remind us that even the grandest structures of the cosmos participate in cycles of renewal, sowing new generations of stars that will shine for billions of years to come. Like gardens tended slowly by unseen hands, galaxies bloom through their collisions, ensuring that the universe never grows barren but remains ever alive with light. The spectacle of colliding galaxies often draws attention to the drama, the great arcs of starlight, the glowing regions of starbirth, and the powerful flares from feeding black holes. Yet all of this is only one part of the story. Collisions do not last forever. After the fireworks fade and the starbursts burn through their fuel, galaxies enter a quieter phase, a long settling process where chaos gives way to calm. What begins as a turbulent dance eventually resolves into a new, unified structure, one that carries the scars of its past yet radiates a sense of stability. The immediate aftermath of a collision is messy. Tidal tails extend far into space, streams of stars are scattered in wide arcs, and gas clouds crash together, lighting up star-forming regions. Over hundreds of millions of years, however, these features begin to dissipate. Tails thin and fade as stars either fall back into the merged system or disperse into the halo. Bridges between galaxies collapse, and the distinct identities of the original spirals blur into one. Gravity, persistent and patient, pulls everything toward balance. As the galaxies merge fully, their delicate spiral structures are often destroyed. Spiral arms, which depend on a thin rotating disk, are disrupted by the violent motions of the collision. Instead of the graceful pinwheels that define spirals, the result is typically a more rounded form, an elliptical galaxy. Ellipticals are smoother, with stars distributed in a broad spheroidal shape rather than in thin, organized disks. Their light tends to be redder, since they contain mostly older stars. The youthful blue glow of starburst regions fades as massive stars live out their brief lives, leaving behind a population of long-lived, cooler suns. This transformation into elliptical form represents a kind of cosmic maturity. The galaxy has survived upheaval, undergone renewal, and emerged as a calmer, more settled structure. In many ways, ellipticals are like the elder statesmen of the galactic world. They no longer produce stars with the vigour of youth, for their gas has been consumed or expelled. Instead, they shine steadily with the accumulated light of ancient stellar populations. They are less flamboyant than spirals, but they carry a quiet dignity, a reminder that stability has its own beauty. The silence of this stage is striking. After the roar of collisions and the blaze of starbursts, the galaxy settles into a long twilight of steady starlight. Without abundant gas, there are few nebulae to glow in vivid colours, few young stars to sparkle in blue brilliance. Instead, the light softens into warmer hues, a cosmic sunset stretching across billions of years. For astronomers, these galaxies appear as golden or reddish ellipses, glowing softly against the blackness of space. They may lack the intricate arms of spirals, but they compensate with a sense of serenity. In galaxy clusters where collisions are more common, elliptical galaxies often dominate. The centres of massive clusters are filled with these giants, swollen from repeated mergers. Some are truly enormous, containing trillions of stars. These central ellipticals act as anchors for their clusters, surrounded by smaller companions and fed by the occasional infall of stray galaxies. Their very size is a testament to their histories. Each one is a patchwork of past unions, their stars gathered from countless predecessors. They are living archives of the universe's restless energy, written in the language of starlight. The calm of elliptical galaxies does not mean absolute stillness. Stars still orbit their centres, black holes continue to lurk in their cores, and faint streams of material may still drift in from smaller galaxies. Yet compared to their earlier lives, these galaxies are far more settled. The tumult has given way to equilibrium. For billions of years they will remain largely unchanged, glowing steadily as their stars age. Their silence is not an absence, but a kind of cosmic contentment. From a human perspective, the long quiet of galaxies after collisions offers a comforting metaphor. Life is filled with moments of upheaval, bursts of energy, and times when everything seems in flux. Yet just as galaxies eventually settle, so too does the universe remind us that calm follows chaos. The elliptical galaxies glowing softly in the night sky are testaments to endurance, to the way systems can find new balance even after profound transformation. The path to this quiet is shaped by physics. During a collision, the motions of stars become scrambled, their orderly rotation replaced by more random orbits. This randomness is why ellipticals lack the neat arms of spirals. The stars no longer follow the coherent paths that maintain a disk. Instead, they move in every direction, filling a volume rather than a thin plane. The result is a galaxy that appears smooth and round, with no preferred orientation. What seems visually simple is the outcome of billions of complex gravitational interactions gradually reaching equilibrium. The loss of gas plays an equally important role. Collisions consume gas in furious bursts of star formation, and some of it is expelled by powerful winds from supernovae and black holes. With little gas left to form new stars, the galaxy's light becomes dominated by older populations. The youthful cycle of birth slows, leaving behind a mature community of suns slowly aging together. Without the drama of starbirth, the galaxy dims slightly, but in exchange it gains stability, shining quietly for billions of years without further upheaval. Some of the most massive elliptical galaxies today are thought to be the end products of countless collisions stretching back to the earliest epochs of the universe. Their immense size, their smooth appearance, and their lack of star-forming regions all point to long histories of growth followed by calm. To look at them is to glimpse the final chapters of galactic evolution, where the once turbulent lives of galaxies conclude in quiet grandeur. The silence of cosmic maturity should not be mistaken for lifelessness. Within elliptical galaxies, stars still live out their individual fates. Some swell into red giants, others collapse into white dwarfs, neutron stars or black holes. Globular clusters still orbit in their halos, and the central black holes may flare occasionally if they capture stray material. Yet the overall rhythm is slower, less dramatic, more measured. If spiral galaxies are youthful dancers in a cosmic ballet, ellipticals are the statues that remain when the music has faded, steady and enduring. This stage of quiet may last for trillions of years, far beyond the lifespan of the universe as we currently observe it. Long after the last spiral galaxies have merged and star formation has ceased, elliptical galaxies will still be glowing faintly with the light of aging stars. They are, in a sense, the ultimate survivors, galactic elders watching over the darkening cosmos. Their calm is not the absence of activity, but the culmination of it, a lasting stability that speaks to the resilience of structure across unimaginable timescales. To reflect on this is to glimpse the universe not just as a place of motion and energy, but also as a place of rest. Collisions bring drama, starbursts bring brilliance, but the quiet aftermath carries its own kind of beauty. The glow of elliptical galaxies is the light of endurance, shining steadily after the tumult has passed. In that light lies a lesson, that even the most violent transformations eventually give way to calm, and that the universe, like life itself, contains not only storms, but also seasons of peace. Far across the night sky, if you look in the direction of the constellation Andromeda, you can see a faint smudge of light. To the unaided eye, it might seem unimpressive, like a blur you could mistake for a cloud or perhaps even a defect in your vision. But that dim patch is in fact the Andromeda Galaxy, the closest large neighbour to our own Milky Way. It is a spiral galaxy like ours, filled with hundreds of billions of stars, and it is on a direct course toward us. In cosmic terms, it is not just visiting the neighbourhood, it is heading straight for our front door. Now, before anyone rushes to cancel their weekend plans, it is important to clarify. This future encounter will not happen for another 4 billion years or so. By that time, the continents on Earth will have shifted into unrecognisable shapes. The sun will be brighter and hotter than it is today, and our species will either be long gone or living in ways that are impossible for us to imagine. The timeline is so vast that it is almost abstract, like being told that a gentle breeze will arrive sometime after the next 1,000 generations of stars are born and die. Still, The idea that two galaxies as immense as the Milky Way and Andromeda are destined to collide is an awe-inspiring thought. Astronomers have been carefully measuring Andromeda's motion, and they know it is moving toward us at about 110 kilometers per second. That may sound like an alarming speed, but when you consider the distance involved, over 2 million light-years, it becomes clear that this is a slow and steady approach. Imagine two ocean liners drifting toward each other across the span of a sea. The distance is so immense that the meeting seems forever postponed, yet the outcome is inevitable. When the collision finally begins, the sight will be spectacular. Anyone around to witness it will see Andromeda grow larger and brighter in the night sky. Over millions of years, it will transform from a faint smudge into a luminous disk that dominates the heavens. Eventually, the two galaxies will interpenetrate, their stars passing through each other like ghosts. The odds of any particular stars colliding are vanishingly small, since they are separated by enormous distances. Instead, the beauty of the event will lie in the slow warping of galactic shapes, in the tidal streams of stars stretched across the sky, and in the blaze of new star formation as gas clouds compress. The merger will not be a sudden crash, but rather a prolonged embrace. The first close pass will throw out great tidal tails, long arcs of stars and dust flung into space. Then, as gravity pulls the galaxies back together, they will fall into one another again and again, each encounter stirring their contents and reshaping their forms. This celestial courtship will play out over billions of years until the two galaxies settle into a single, larger structure. Astronomers predict that the result will likely be an elliptical galaxy, rounder, smoother, and far bigger than either of its parents. Sometimes it is referred to as Milkomeda, a playful combination of the two names. One of the most fascinating aspects of this future merger is considering what will happen to our own solar system. It is unlikely to be destroyed, but its position within the galaxy could change dramatically. Our sun and planets might be flung farther from the galactic centre, or perhaps drawn closer. We could even find ourselves in the middle of a tidal tail, drifting through a sparse stream of stars stretched thin across space. For any future descendants of humanity, whether they live on Earth, Mars, or some yet unimagined world, the view of the sky could be transformed beyond recognition. The familiar patterns of constellations would be erased, replaced by strange new arrangements as stars shift positions in the cosmic shuffle. From Earth's surface, if it is still habitable then, the sight would be unlike anything our species has ever known. Imagine looking up at night to see two great spiral disks overlapping, their arms weaving together in glowing threads of starlight. Imagine the glow of starburst regions so bright that they outshine the usual backdrop of galaxies. It would be a sky alive with motion, though motion measured on timescales so slow that no human life could perceive it. Generations would pass, civilizations rise and fall, and still Andromeda's shape would only gradually change from decade to decade. The drama would belong to the cosmos itself, unfolding with the patience of eternity. The collision of the Milky Way and Andromeda also tells us something important about the universe. It reminds us that galaxies are not isolated islands, but participants in a cosmic web of interactions. Gravity ensures that no galaxy is truly alone. Over long enough timescales, neighbours will drift together, collide and merge, creating new forms from old. Our own galaxy's fate is not unique. It is part of a grand pattern, one that has played out countless times across the universe. The heavens are filled with the remnants of past unions, with elliptical galaxies that bear silent testimony to collisions long past. There is also something humbling about realising that the Milky Way, with all its familiar constellations and its quiet spiral arms, is only temporary. We live in a snapshot of cosmic history, a moment when our galaxy has its graceful shape and its familiar neighbours. In a few billion years, that snapshot will be gone, replaced by a new scene in which the Milky Way as we know it no longer exists. The stars will still shine, but the stage on which they shine will have been entirely rebuilt. If there is humour to be found in all of this, it lies in the scale. People worry about daily schedules, weekend plans, or the slow loading of a video online. Yet the universe has already penciled in a meeting between two galaxies, an encounter so immense it will reshape hundreds of billions of stars, and the best part is that it is set to begin in 4 billion years, give or take a few hundred million. That is as gentle a deadline as the cosmos ever gives, and it certainly leaves time to finish whatever errands one might have this week. The thought of Andromeda on the horizon is not something to fear, but something to marvel at. It is a reminder of the living, evolving universe we inhabit. It tells us that change is woven into the fabric of the cosmos, and that even galaxies must eventually transform. Our Milky Way's future may be written in the slow approach of Andromeda, but the story is not an ending. It is a continuation, a renewal, a reshaping into something larger and grander. So when you gaze up at the faint smudge of the Andromeda Galaxy, remember that you are looking at destiny in progress. That soft light has already travelled more than 2 million years to reach your eyes, and behind it lies a motion so vast and steady that it will one day alter the very shape of our home galaxy. The horizon of time is long, but the meeting is inevitable. Two star cities drifting together across the deep will one day unite, and from their union a new galactic form will rise, glowing silently in the endless night. If there is one thing humanity has become rather good at, it is simulating the future. From predicting the weather to charting the motion of planets, computers have become our crystal balls, showing us what might unfold given the laws of nature. When it comes to the cosmic future of our own Milky Way galaxy, astronomers have used simulations to peek billions of years ahead, watching in fast forward as our spiral home slowly drifts into its great neighbour, the Andromeda Galaxy. These simulations reveal a story that is both dramatic and strangely elegant, a preview of a performance our descendants may never see in person, but which we can already understand in detail. The key to building these simulations is physics. Galaxies are not random clouds of stars, they are bound by gravity, shaped by the unseen scaffolding of dark matter, and influenced by the momentum of their own motions. Every star, every cloud of gas, every halo of invisible matter is tugged and pulled by gravity's quiet hand. To simulate a galactic merger, astronomers start with what we know about the structure of both the Milky Way and Andromeda, their masses, their shapes, and their velocities. Into powerful computers, they feed these values and then let Newton's and Einstein's equations run the show. What unfolds on the screen is not an artist's guesswork, but the mathematical choreography of gravity itself. The results are astonishing. In simulations, Andromeda does not simply slam into the Milky Way and stop. Instead, the galaxies weave through one another in a long, drawn-out embrace. On their first close pass, gravitational tides pull out long streams of stars, stretching them into arcs that glitter across space. The galaxies then recoil, pulled back by their mutual attraction, before swinging together again. This cosmic dance repeats, each encounter stripping away more structure, until at last the two galaxies coalesce into one. From beginning to end, the process takes several billion years, an eternity by human standards, but just a natural cycle for the universe. One of the most fascinating outcomes of these simulations is that stars within the galaxies remain largely unharmed. It is easy to imagine stars smashing together in a fiery crash, but space is spacious. Even within galaxies, the average distance between stars is so great that direct collisions are incredibly unlikely. Instead, stars glide past each other, their paths nudged by the shifting gravitational field of the merger. A star that once orbited the centre of the Milky Way might find itself flung outward, or pulled into a different orbit altogether, but it survives the encounter intact. To a star, a galactic collision is more of a gentle rearrangement than a disaster. For Earth and the Sun, simulations suggest that survival is not only possible but probable. Our solar system may be thrown onto a wider orbit, or drift into a tidal stream, but it is unlikely to be destroyed. Of course, Whether Earth itself is still habitable by that point is another question entirely. In 4 billion years, the sun will be brighter than it is today, gradually heating Earth and potentially boiling away its oceans. The climate will change beyond recognition, perhaps long before the galaxies ever make first contact. If life still exists by then, it will either have adapted to extreme conditions or moved on to new worlds. Still, the view of the sky during the merger would be extraordinary, a changing canvas of stars unlike anything humanity has ever known. Simulations allow us to picture this transformation in stunning detail. Astronomers have watched virtual Milky Ways collide with virtual Andromedas, each pixel of starlight representing millions of suns. They can spin the view from any angle, showing what the galaxies look like as seen from inside or from far outside as a cosmic spectator. In many of these digital previews, the Milky Way loses its delicate spiral arms, torn and twisted until they resemble ribbons drifting in the wind. Andromeda too is stripped of its familiar shape. What emerges after countless simulated encounters is not a spiral at all, but an elliptical galaxy, a great rounded ball of stars with no arms at all, only a smooth glow. This eventual galaxy even has a proposed name, Milkdromeda, a playful blend of Milky Way and Andromeda. Some call it Milkomeda, but either way it is destined to be a heavyweight. It will contain more than 1 trillion stars, perhaps double the combined population of its parents. It will shine brighter, stretch wider, and dominate its corner of the universe. From the perspective of cosmic history, the merger is simply one more step in a long line of galactic unions, each shaping the landscape of the universe. But for us, living within one of the participants, it feels like a personal destiny. Another remarkable detail revealed by simulations is the role of dark matter. Though invisible, dark matter accounts for most of the mass of both galaxies. It forms vast halos around them, extending far beyond the visible stars. When the Milky Way and Andromeda merge, it is these halos that collide first, overlapping and blending together like two ghostly spheres. Their gravity then drags the visible galaxies toward one another, ensuring the union is inevitable. Without dark matter, the two galaxies might simply pass by, like ships missing each other in the night. Instead, they are bound together by invisible chains. It is not only Andromeda that will be part of the story. Our smaller companion galaxies, the Magellanic Clouds, the Triangulum Galaxy, and many faint dwarf galaxies are also caught in the gravitational web. They too may be drawn into the merger, either swallowed whole or scattered across the tidal streams. The final Milkdromeda will be a composite, not just of two great spirals, but of many smaller companions folded into its bulk. Like a family tree with countless branches, the future galaxy will carry the legacy of every smaller system it consumed along the way. There is poetry in the way simulations reveal these vast futures. On a computer screen, billions of years unfold in minutes. A spiral galaxy spins like a pinwheel, collides with its neighbour, and reshapes itself before your eyes. What would be unobservable in a human lifetime becomes a story told in glowing trails of light. These models are not just scientific tools, but windows into the destiny of the cosmos. They remind us that the universe is always in motion, always evolving, and always ready to surprise us with its capacity for grandeur. And in the midst of all this, one cannot help but feel a kind of cosmic humility. Here we are, running models of the next 4 billion years, while most of us have trouble planning for the next 4 days. Yet the ability to simulate such vast futures is a triumph of human curiosity and intellect. From tiny equations scribbled on paper to supercomputers crunching trillions of calculations, we have built a way to see into the universe's tomorrow. When the Milky Way and Andromeda finally merge, there will be no audience in the traditional sense. Stars will not stop to applaud, nor will galaxies elsewhere pause to take note. The event will simply happen as countless mergers have happened before, as countless more will happen after. But through our simulations, we have already witnessed it. We already know the broad strokes of how the story will unfold. The The stretching of arms, the birth of tidal tails, the settling into a luminous elliptical form. Milkdromeda will rise, glowing softly in the dark, a monument to the inevitability of cosmic change. And perhaps that is the most beautiful part of all. By simulating the future, we not only glimpse what is to come, we also learn to see our present more clearly. The Milky Way we live in, with its spiral arms and its starry rivers, is a fleeting stage in a longer journey. One day the patterns we know will be gone, folded into a new creation, and yet, even knowing this, there is comfort. Stars endure, galaxies evolve, and the universe continues its endless dance with or without us to watch. In the vast sweep of cosmic history, collisions have been less an occasional drama and more a constant feature of galactic life. To understand this, it helps to travel back in imagination to the early universe, a time not long after the Big Bang. Roughly 13.5 billion years ago, matter had not yet had time to spread out very far. The universe was smaller, denser, and more tightly packed. Galaxies, such as they were not the great sweeping spirals and ellipticals we know today. Instead, they were small, clumpy structures, brimming with gas and forming stars at a frantic pace. And because the distances between them were relatively short, collisions were inevitable and frequent. These early galaxies were like seedlings sprouting in a crowded garden, with so little space, their roots and branches constantly tangled. Astronomers studying the farthest reaches of the universe with telescopes like Hubble and the James Webb Space Telescope often see galaxies that look warped, irregular, or chaotic. These are not cosmic accidents of poor design. They are snapshots of galaxies in the process of growing, colliding, and merging. What looks like a galactic mess is actually the raw energy of construction, the universe building the large galaxies that dominate today's skies. Collisions in this youthful cosmos were not gentle affairs. Because galaxies were smaller and more gas-rich, when they collided, enormous bursts of star formation followed. Gas clouds slammed together, compressing under gravity and igniting into waves of new stars. These events, called starbursts, created dazzling clusters of massive short-lived stars that would explode as supernovae only a few million years later. The fireworks were both beautiful and violent, reshaping the galaxies that hosted them. Over time, the constant cycle of merger and starburst transformed small, irregular systems into larger, more organized galaxies. It is a process astronomers sometimes call galactic assembly. Just as humans build cities not all at once, but through the accumulation of smaller towns, the universe built great galaxies by gradually fusing smaller ones. Every galaxy we see today is the result of countless collisions and mergers. Even the most majestic spiral galaxies have a rough history hidden within their stars. If you could peel back their layers, you would find evidence of swallowed companions, streams of stars torn from smaller galaxies, and scars left by past encounters. Our own Milky Way is no exception. In fact, the halo of stars surrounding the Milky Way contains remnants of ancient galaxies that were absorbed billions of years ago. Astronomers can identify these lost siblings by their stars' chemical fingerprints. Stars born in different galaxies often carry unique blends of elements, depending on the history of supernovae and star formation in their birth environments. By studying these stellar fingerprints, researchers have pieced together the Milky Way's family tree. It turns out our galaxy has already consumed dozens of smaller companions throughout its long history. We are, quite literally, a collection of cosmic leftovers stitched into a single spiral form. The role of collisions in shaping the cosmos cannot be overstated. Without them, galaxies would likely have remained small and irregular, scattered like crumbs across the universe. Instead, mergers allowed galaxies to grow massive, gathering enough material to form orderly structures. Spirals with their elegant arms arose as gas settled into rotating disks after collisions. Elliptical galaxies, by contrast, often formed when two spirals merged violently, scrambling their stars into rounded, featureless distributions. In this way, the universe sculpted variety from chaos, giving rise to the rich galactic zoo we observe today. Interestingly, collisions also played a central role in distributing heavy elements. The first stars in the universe formed almost entirely from hydrogen and helium, the simplest ingredients forged in the Big Bang. It was through supernovae, especially those triggered by starbursts in colliding galaxies, that heavier elements like carbon, oxygen, and iron were scattered across space. These elements enriched future generations of stars and eventually planets. Without galactic collisions stirring the pot and triggering waves of star formation, the universe might never have become chemically diverse enough to produce life as we know it. In this sense, cosmic violence paved the way for cosmic fertility. Another remarkable effect of collisions in the early universe was the growth of supermassive black holes. Many galaxies host these titans at their centres, some with masses millions or billions of times that of the Sun. But such black holes did not form fully grown. They began as smaller seeds, perhaps the remnants of massive stars or dense clusters of matter. When galaxies collided, their central black holes were fed with torrents of gas funneled inward by gravitational disruption. These feeding frenzies allowed black holes to bulk up rapidly, becoming the colossal anchors we see today. In some cases, mergers even brought black holes together, forming binaries that spiraled inward until they coalesced. These dramatic events sent ripples of gravitational waves across the fabric of space-time, echoes that modern detectors like LIGO and Virgo are only now beginning to catch. The evidence for this violent, collision-rich past is everywhere if one knows where to look. Deep surveys of the sky show galaxies at various stages of merging, from early encounters with faint tidal bridges to fully blended ellipticals that hide their chaotic origins. Closer to home, faint streams of stars arc around the Milky Way, ghostly remnants of galaxies that were shredded and absorbed. The Andromeda Galaxy, too, carries scars of past collisions, with loops and shells of stars encircling its disk like ripples in a pond. These features are cosmic fossils, silent witnesses to the ceaseless collisions that built the universe's architecture. What is most humbling about this story is the scale of time. In the early universe, collisions were almost routine, occurring over spans of hundreds of millions of years. To us, that sounds impossibly long, but on cosmic terms, it was a fast and furious era. As the universe expanded and galaxies grew larger, collisions became less frequent, though still inevitable. In the present day, galaxies are more widely spaced, but their fates remain intertwined. The great mergers may unfold slowly, yet they are certain, governed by gravity's patient persistence. Looking back across cosmic time is a bit like watching the universe grow up. The early cosmos was a rowdy, crowded playground, full of youthful galaxies bumping into one another and throwing star-forming tantrums. Over billions of years these galaxies matured, settling into more stable forms, though their restless natures never completely disappeared. Even now, collisions continue, though on grander scales, and with more subtlety than before. The universe has not outgrown its penchant for rearranging itself. It has merely slowed its pace. In reflecting on this grand history, one might say that collisions are not disruptions, but engines of creation. They drive the growth of galaxies, enrich the cosmos with the elements of life, and ensure that the universe remains dynamic rather than static. Every star, every planet, and every living being is, in a sense, the product of this long chain of galactic encounters. To look up at the night sky is to see the outcome of billions of years of cosmic collisions woven together into the galaxies that now shine serenely overhead. The quiet beauty of the present universe hides a past of turbulence, but it is a turbulence that made beauty possible. Without the collisions of galaxies in the early cosmos, there might be no great spirals to admire, no stable planets to inhabit, and no beings to ponder the story of it all. It is a reminder that even the most chaotic processes can yield order, and that from the jostling of countless galaxies came the grand architecture of the universe itself, When galaxies collide, the drama is often described in terms of sweeping arcs of stars, great rivers of gas, and vast shifts in shape. But beneath that grandeur lies a more intimate tale, one that plays out within the hearts of individual stars. Every star, regardless of whether it is caught in the midst of a cosmic collision or left floating in quiet isolation, is bound by its own internal clock. Its fate is written in the balance of gravity pulling inward and nuclear fusion pushing outward. In this sense, galactic collisions may shape the dance floor, but stars themselves carry the rhythm of their own lives. To appreciate the role of stars in collisions, one must first understand their natural life cycle. Stars form when cold clouds of hydrogen gas collapse under their own gravity, heating up until nuclear fusion ignites in their cores. For most of a star's life, it is remarkably steady, fusing hydrogen into helium in a delicate balance. The Sun, for instance, has been doing this for about 4.5 billion years, and is expected to continue for roughly another 5 billion. This stage is called the main sequence, and it is a period of stability where stars shine with consistent brightness and provide energy to whatever planets might circle them. But nothing in the universe lasts forever, and stars are no exception. When the fuel in a star's core begins to run low, change is inevitable. For stars like our Sun, the next stage is a transformation into a red giant. As hydrogen becomes scarce, fusion slows, and gravity begins to win. The core contracts, heating up, while the outer layers puff outward into a swollen, luminous form. A star that was once modest in size can expand to engulf nearby planets. If the Sun were to expand in this way today, it would grow large enough to consume Mercury, Venus, and possibly Earth. To an observer far away, the star would look like a glowing ember of extraordinary size shining in deep red hues. Red giants are both endings and beginnings. As they expand, they shed their outer layers into space, creating shells of gas that drift away like ghostly halos. These shells, illuminated by the fading light of the star's core, form what are known as planetary nebulae. Despite the misleading name, they have nothing to do with planets. Instead, they are reminders of stellar mortality, hauntingly beautiful clouds that can shine for tens of thousands of years before dispersing completely. In their fading glow, we see the recycling of cosmic material, enriching the galaxy with heavier elements forged during the star's life. At the heart of a planetary nebula lies the remnant of the star itself, a white dwarf. These objects are stellar corpses, incredibly dense, and no longer powered by fusion. A white dwarf may be no larger than Earth, yet it contains the mass of a sun-like star. Their surfaces glow with residual heat, but over billions of years they cool and fade, eventually becoming black dwarfs, objects so faint they no longer shine. None yet exist, because the universe itself is not old enough. Every white dwarf still glows faintly, like embers at the bottom of a cosmic fireplace. For more massive stars, the ending is more violent. Stars, many times the mass of the Sun, live much shorter lives, burning through their fuel with reckless intensity. Instead of quietly puffing into red giants, these titans swell into red or blue supergiants, colossal behemoths that burn fiercely but briefly. When their fusion processes can no longer sustain them, gravity delivers a final, crushing blow. The core collapses in on itself, while the outer layers are expelled in a brilliant supernova explosion. In an instant, the star releases more energy than an entire galaxy does in a year. Supernovae are among the most spectacular events in the universe, visible across millions of light years. They not only signal the death of a star, but also sow the seeds for new beginnings. In their explosive chaos, they scatter heavy elements such as carbon, oxygen, silicon, and iron across space, materials that will one day form planets, oceans, and living beings. If a galaxy is a gardener, then supernovae are its seed scatterers, flinging the ingredients of life far and wide. The core that remains after a supernova depends on the star's original mass, If it was relatively modest, it may collapse into a neutron star. These are extraordinary objects, only about 20 kilometers across yet containing more mass than the Sun. A teaspoon of neutron star matter would outweigh mountains. Neutron stars are so dense that their surfaces warp light, and they spin at dizzying speeds, sometimes hundreds of times per second, sweeping beams of radiation into space like cosmic lighthouses. If the star was even more massive, its core may collapse beyond all resistance, forming a black hole. In this case, gravity overwhelms every other force, pulling matter into a region so dense and compact that not even light can escape. Black holes born from supernovae may be only a few times the mass of the Sun, yet their influence extends far beyond their size, shaping the galaxies around them and, in collisions, playing a central role in galactic evolution. In galactic collisions, these stellar fates do not change dramatically. Stars remain too far apart to collide directly, and their lifespans unfold according to their mass and structure. However, collisions do influence how many stars are born and where. When galaxies merge, vast clouds of gas are compressed, leading to bursts of star formation. These newborn stars inherit the long arc of stellar destiny, destined to shine, expand, and eventually die, just as countless others have before. Collisions in this sense act as a trigger, setting off whole new generations of stars, each with its own story of transformation. Over billions of years, the interplay between collisions and stellar evolution has woven a tapestry of creation and destruction. Many of the stars we see in the night sky today were likely born in such turbulent environments. Some may one day explode as supernovae, sending out the heavy elements that will enrich yet another round of star formation. Others will quietly fade into white dwarfs, contributing to the silent glow of galactic halos. There is something deeply reflective about contemplating these stellar fates. Unlike galaxies, which can live for tens of billions of years, stars are comparatively fleeting. They flare into being, shine for their allotted span, and then transform into something new. And yet their endings are never wasted. The material they return to space becomes the raw ingredients for future stars and planets. Every ending is a beginning, every death a step toward new creation. In this light, galactic collisions are less about destruction and more about renewal. They shake the cosmic snow globe, stirring gas and dust, lighting the match for starbirth, and setting countless stellar lives into motion. Within those lives lie the quiet dramas of red giants swelling, white dwarfs fading, neutron stars spinning, and black holes silently consuming. The universe has always been a patient recycler. Nothing is truly lost, only transformed. The atoms in our bodies were forged in ancient stars that ended their lives billions of years ago, perhaps in galaxies long since merged and reshaped. When one reflects on the fate of stars, especially in the context of galactic collisions, it becomes clear that the cosmos is not a place of simple endings, but of perpetual change. Stars may burn out, galaxies may collide, but from the debris comes life, light, and the continuing story of the universe. This slow meditation on the lives of stars reminds us of something profound. Even in the grandest collisions, the fate of stars is written not in chaos, but in continuity. Each star's journey is a thread, and collisions simply weave those threads into ever larger and more intricate patterns. What seems like an ending is always the beginning of something new, a lesson written into the very fabric of the cosmos. When astronomers first began to study galactic collisions in detail, they expected to see the familiar forces of gravity and gas dynamics doing most of the work. Stars would drift past one another, gas clouds would slam together, and galaxies would eventually merge into new shapes. But as telescopes became more advanced, and techniques for mapping mass distribution improved, a curious pattern emerged. Something invisible seemed to be shaping these events, something far more massive than the stars and gas combined. This hidden hand was dark matter, the silent framework of the universe. Dark matter does not shine, reflect, or absorb light. In fact, it does not interact with light at all, which makes it invisible to even the most powerful telescopes. Its presence is known only through gravity, tugging at stars, bending light from distant galaxies, and holding together structures that would otherwise fly apart. In the case of colliding galaxies, dark matter plays a starring role. Without it, the drama of cosmic collisions would look very different, and the universe as we know it would likely not exist. The clearest example of this comes from a system known as the Bullet Cluster. Located about 3.8 billion light-years away, the Bullet Cluster is the aftermath of two galaxy clusters colliding at high speed. A galaxy cluster is already an enormous structure, containing hundreds of galaxies bound together by gravity. When two of these colossal swarms collide, it becomes a natural laboratory for studying the unseen scaffolding of the cosmos. What makes the Bullet Cluster so extraordinary is that it provided direct, observable evidence for dark matter's existence. Using X-ray telescopes, astronomers mapped the hot gas that fills the cluster, which glowed brightly as the collision heated it to millions of degrees. This gas accounts for the majority of the visible matter in galaxy clusters, far outweighing the stars themselves. During the collision, the gas clouds from each cluster slammed into one another, slowing down and piling up between the two clusters like cars in a traffic jam. But when astronomers used a technique called gravitational lensing to map the mass distribution in the cluster, they found something astonishing. Gravitational lensing occurs when light from more distant galaxies is bent by the gravity of the intervening mass. By studying the way background galaxies appeared stretched and distorted, researchers could create a map of where the mass was located. That map revealed that most of the mass had passed straight through the collision and was sitting around the galaxies themselves, not in the hot gas that had piled up. This meant that while the visible matter, the hot gas, had slowed down during the collision, most of the mass had not interacted at all. It simply glided through, unaffected. This invisible mass lined up with where the galaxies were, showing that there was far more matter present than what could be accounted for by stars and gas alone. The conclusion was inescapable. Dark matter must exist, acting as a ghostly companion to galaxies, shaping their evolution yet never directly colliding. The Bullet Cluster became one of the most compelling pieces of evidence for dark matter. It showed, quite literally, a separation between the visible matter and the bulk of the mass. Without dark matter, the lensing patterns would have matched the glowing hot gas. Instead, the lensing map revealed invisible clumps of matter that betrayed the presence of something unseen. For many astronomers, this was the smoking gun. Collisions like this reveal a crucial property of dark matter. It hardly interacts with itself. While ordinary matter collides, heats up and slows down, dark matter seems to glide through other dark matter halos without much friction. This behavior suggests that dark matter is made of particles that rarely, if ever, collide with one another, interacting only through gravity. This is why galaxies are able to pass through each other in a collision without their dark matter halos shattering. It is as though the galaxies are wrapped in invisible cocoons that overlap but never tangle. Dark matter is not just a background player in galactic collisions, it is the stage itself. Galaxies are embedded in massive dark matter halos, and these halos provide the gravitational framework that holds them together. Without dark matter, galaxies would not have enough mass to keep their stars from drifting away. Spiral galaxies, for instance, rotate much faster than their visible matter alone should allow. Without the extra gravity from dark matter, they would fling themselves apart like a spinning pizza dough tossed too thin. During collisions, dark matter shapes the trajectories of galaxies and the final form of the merger. It provides the gravitational pull that keeps galaxies bound even as their gas is stripped, their stars flung outward, and their shapes distorted. The eventual elliptical galaxy that forms from a merger is essentially sculpted inside the invisible cocoon of dark matter, which acts as both container and guide. The bullet cluster is not the only case where dark matter has revealed itself through cosmic collisions. Other cluster collisions, such as the Trainwreck Cluster, also known as a Bell 520, show unusual distributions of dark matter that have puzzled astronomers. In some cases, dark matter seems to clump in unexpected ways, challenging simple models and hinting that there may be more complexity to its nature than originally thought. Each collision observed becomes a test case for understanding this mysterious component of the universe. What is especially humbling is that dark matter makes up about 85% of all matter in the universe, yet it remains unseen and largely mysterious. Everything we can see, stars, planets, galaxies, gas clouds, makes up only a small fraction of the cosmic inventory. In this light, the visible universe is more like the foam on the crest of a wave, while dark matter is the deep ocean beneath, shaping the swell but hidden from sight. Collisions provide one of the few opportunities to watch dark matter in action. When galaxies and clusters pass through each other, the visible matter behaves one way and the dark matter another, and the separation gives us clues. By mapping many such events, astronomers hope to narrow down what dark matter actually is. The leading candidates are exotic particles that interact only weakly with ordinary matter, sometimes called WIMPs, or weakly interacting massive particles. Others propose lighter particles such as axions. Whatever the case, the evidence from collisions strongly supports the existence of something beyond what we can see. In reflecting on these discoveries, one can see dark matter as the silent architect of cosmic structure. It does not light up the sky, it does not blaze in supernovae, and it does not form the stars that shine in the night. Yet without it, galaxies would never have formed in the first place. Collisions, with all their dramatic beauty, are shaped by its presence. The arcs of stars, the bursts of starbirth, and the eventual quiet settling of galaxies into new forms all happen inside a dark matter framework. It is almost poetic that something so invisible could be so essential. The bullet cluster showed us that the universe has layers we cannot see, and that collisions can reveal the outlines of this hidden architecture. While gas crashes and glows, while stars pass silently by, dark matter drifts through, unbothered, steady, and strong. It is the quiet foundation upon which the cosmic dance unfolds, the unseen partner guiding galaxies through their long and tangled waltz. In the end, galactic collisions remind us of just how little of the universe we truly see. The light from stars dazzles, but the real mass lies in shadow. Dark matter, elusive and mysterious, may not reveal its face, but its hand can be traced in the arcs of galaxies, in the bending of distant starlight, and in the enduring structures of the cosmos. Through the violence of collisions it whispers its presence, steady and silent, shaping the universe from behind the curtain. When galaxies collide, the spectacle often appears to be about stars, gas, and the grand reshaping of spiral arms into long tidal tails. Yet hidden at the very core of these encounters lies another drama, one that is quieter to the eye but enormously powerful. This is the story of supermassive black holes, the giants that lurk at the centre of most galaxies. Normally they sit in relative calm, feeding only sparingly on stray gas and dust. But when two galaxies crash together, the cosmic buffet is suddenly open, and these black holes can gorge themselves in a way that transforms not only their own growth, but also the brightness of their host galaxies. At the heart of nearly every large galaxy, including the Milky Way, resides a supermassive black hole, with a mass ranging from millions to billions of times that of the Sun. Despite their reputation as voracious consumers, most of the time they are surprisingly quiet. Our own galaxy's central black hole, Sagittarius A star, is a fairly subdued diner, nibbling gently rather than feasting. But when galaxies merge, the story changes dramatically. Gas and dust that once orbited quietly in well-behaved disks are stirred into chaos. Gravitational forces tug on these reservoirs of material, funneling them inward toward the galactic centres. This inflow is crucial, Black holes do not eat stars directly very often. The distances between stars are simply too vast. What they feast on is gas and dust, and galaxy collisions provide an enormous delivery system. The same tidal forces that stretch out long stellar tails also act as conveyor belts, driving interstellar matter into the inner regions of the galaxies. As this material spirals in, it forms an accretion disk around the black hole. Friction within the disk heats the gas to millions of degrees, releasing immense amounts of energy before it crosses the event horizon. The result is the birth of an active galactic nucleus, or AGN. These are among the brightest objects in the universe, outshining all the stars in their host galaxies combined. When a supermassive black hole feeds heavily, the disk around it radiates across the spectrum, from radio waves to visible light to high-energy X-rays. Some even launch powerful jets that extend for thousands of light-years, spearing through intergalactic space. These jets are powered not by material falling into the black hole but by magnetic fields, twisted and amplified by the swirling disk. The most extreme examples of this phenomenon are quasars. In the 1960s, astronomers were puzzled by these quasi-stellar objects, which appeared like faint stars but emitted astonishing amounts of energy. Only later did it become clear that quasars are the blazing hearts of galaxies whose central black holes are consuming matter at a furious pace. Quasars shine so brightly that they can be seen across billions of light-years, acting as cosmic lighthouses from the early universe. Collisions are the perfect trigger for this quasar phase. Alone, many galaxies lack the mechanism to channel large amounts of gas into their centers. Spiral galaxies like the Milky Way maintain ordered rotations that keep material spread out across vast disks. But smash two galaxies together, and all that order is gone. Gas is shocked, compressed, and redirected inward. Black holes suddenly have more than enough fuel to binge, and in doing so, they light up the universe. One might expect that two merging galaxies with supermassive black holes would immediately result in two active nuclei blazing side by side. In some cases, this does happen, and astronomers have observed so-called dual AGN systems, where both black holes are actively feeding during the early stages of a merger. Over time, though, the black holes are drawn together by dynamical friction, gravitational interactions with surrounding stars and gas that slowly sap their orbital energy. Eventually, they spiral toward one another, forming a close pair. When they finally merge, they unleash ripples in space-time called gravitational waves, though these are at frequencies far lower than what current detectors can catch. But before that dramatic finale, the black holes enjoy their period of plenty. During this phase, the galaxies themselves can be transformed. The energy released by accreting black holes is not limited to light. It also includes winds and radiation powerful enough to push gas away. This process, called feedback, can regulate star formation across the galaxy. In some cases, the central active galactic nucleus drives out so much gas that the galaxy's ability to form new stars is quenched, leaving behind a more passive elliptical galaxy. In others, the interaction between jets and gas clouds can actually compress matter, triggering new starbirth. This interplay between feeding black holes and galaxy growth is one of the most fascinating areas of astrophysics. It suggests that black holes are not just passengers in the story of galaxies, but co-authors. Their growth during mergers shapes the fate of their hosts. The bigger the galaxy, the bigger the black hole tends to be, and collisions help establish this link. When galaxies collide and merge, their central black holes eventually do too, creating an even larger one that sits at the heart of the newly formed galaxy. The timing of these events matters as well. In the early universe, collisions were more common, and the abundance of gas was far higher. This is why quasars are often seen at great distances, which means we are observing them as they were billions of years ago. Back then, galaxies were small, gas-rich, and prone to frequent mergers. Their central black holes had plenty of opportunities to feast, growing rapidly to billions of solar masses in a relatively short cosmic time. Today, galaxies are larger, more mature and poorer in gas, so quasars are rarer. Even so, nearby collisions still produce their own dramatic displays. The antennae galaxies, about 45 million light-years away, are two spirals in the midst of merging. While their central black holes are not as flamboyant as the most distant quasars, the inflow of gas has created starbursts and may yet trigger stronger AGN activity as the merger continues. Our own Milky Way and Andromeda, destined to collide in about 4 billion years, each host a central black hole. When they merge, it is likely that both will be fed by the inflowing material, possibly igniting a quasar-like phase before they finally coalesce into a single, much larger black hole. The idea that collisions can make galaxies shine brighter is both literal and metaphorical. Literally, the radiation from an active black hole can turn a once ordinary galaxy into a beacon, visible across cosmic distances. Metaphorically, these events remind us that destruction and creation are two sides of the same coin in the universe. Collisions disrupt and dismantle, but they also feed black holes, trigger starbursts and reshape galaxies into new forms. Out of chaos emerges brilliance, sometimes so intense that it outshines everything else in the cosmos. It is tempting to think of black holes as cosmic monsters lurking in the dark, waiting to devour everything. But in truth, they're more like reluctant eaters, mostly quiet until circumstances deliver a feast. Galactic collisions provide those circumstances. When the meal arrives, the transformation is profound, not just for the black hole, but for the entire galaxy around it. Quasars and active galactic nuclei are the outward signs of this hidden banquet. Spectacular reminders that even the darkest objects in the universe can, under the right conditions, become sources of extraordinary light. In the quiet stretches of space, black holes may slumber for eons, but when galaxies collide, they awaken. They feed, they grow, and they shape the destiny of their hosts. And in doing so, they remind us that the universe is a place where even the most destructive forces can give rise to brilliance. Galactic mergers, far from being only violent encounters, are also opportunities for black holes to write their chapter in light, turning the deep night of the cosmos into a stage lit by their extraordinary hunger. When imagining galaxies, it is easy to picture them as lonely islands adrift in the vast ocean of space, sailing silently through the darkness. Yet the reality is far more intricate and connected. Galaxies are not solitary wanderers, but members of families, congregating in groups, clusters, and even sprawling superclusters that stretch across unimaginable scales. When galaxies collide, the drama is not an isolated performance, but a small act within a grander play, part of the vast tapestry that astronomers call the cosmic web. This web is not just a poetic idea, it is a literal structure revealed by some of the largest surveys of the universe ever undertaken. Mapping the positions of hundreds of thousands of galaxies shows that they are not sprinkled randomly across the cosmos. Instead, they form filaments, long strands of galaxies and dark matter that snake across the universe, intersecting at dense knots where clusters form. These filaments are separated by immense voids, regions where galaxies are rare and space is hauntingly empty. Seen on such a scale, the universe looks like a colossal three-dimensional spiderweb, glowing faintly with galaxies instead of dew. The Milky Way itself belongs to a modestly sized gathering called the Local Group, which contains a few dozen galaxies bound together by gravity. Among its members are the familiar Andromeda and the smaller Magellanic Clouds, along with many dwarf galaxies quietly orbiting in the shadows. This group is only a tiny thread in the much larger Virgo supercluster, which itself is just one section of the Laniakea supercluster, a vast continental-like feature of the cosmic web that spans over 500 million light-years. When collisions occur in our little corner, they are ripples in this grander interconnected sea. Understanding collisions within this context makes them feel less like accidents and more like inevitabilities. In crowded neighborhoods of the cosmos, galaxies are bound to interact. Within clusters, where hundreds or even thousands of galaxies share the same space, encounters are frequent. The gravitational pull of the cluster as a whole herds its members into a tight space, and in this environment, galaxies are constantly tugged, twisted, or stripped of their gas. Some encounters are gentle flybys, while others are full mergers that reshape the galaxies involved. Clusters themselves are fascinating structures. They are not just collections of galaxies, but also vast reservoirs of hot plasma, known as the intracluster medium, which glows in X-rays and holds more mass than all the stars in the galaxies combined. When galaxies collide within these environments, the hot medium adds its own drama, slowing them down, stripping their gas, and influencing how they evolve. The famous Bullet cluster, for example, shows two clusters colliding in spectacular fashion. The galaxies within each cluster mostly pass through unscathed, but the hot gas slams together, leaving a shock wave that looks like a cosmic bullet. On even larger scales, superclusters are less tightly bound. They are like vast archipelagos of clusters and groups, connected by filaments that stretch across hundreds of millions of light years. Here, collisions still occur, but the timescales are staggeringly long. These structures remind us that galaxies are never entirely alone. Even the most isolated-looking galaxy in the sky is still part of some filament, still woven into the web of cosmic structure. What is remarkable is that the pattern of the cosmic web echoes processes that began shortly after the Big Bang. In the early universe, slight differences in density, so small they were just tiny fluctuations in the smooth sea of matter and energy, grew under the influence of gravity. Areas with slightly more matter pulled in more material, becoming filaments and clusters, while areas with less became voids. Over billions of years, this uneven distribution blossomed into the intricate network we see today. The collisions and mergers of galaxies are one of the natural consequences of this growth. The cosmic web, forever reshaping itself as matter, flows along its filaments toward the densest regions. There is a certain serenity in realizing that what seems chaotic, the crashing of galaxies, the birth of stars in collisional starbursts, the violent feeding of black holes, is actually part of a grand pattern that has unfolded for billions of years. Every act of violence in space is counterbalanced by the quiet order of the web, a structure so vast that even the largest galaxies are only grains of dust within it. Collisions, instead of being disruptive exceptions, are the threads weaving galaxies more tightly into this fabric. It is also humbling to reflect on how our own existence is tied to this interconnectedness. The Milky Way's history has been shaped by past mergers. Our galaxy carries the remnants of smaller galaxies it has absorbed, their stars now woven into its halo. The elements forged in those ancient stars, scattered during mergers, became part of the material that would one day form the Sun, Earth, and life itself. Even human beings, contemplating the cosmos with quiet wonder, are products of this immense cosmic web. The image of the web invites reflection beyond science. Just as galaxies are linked in filaments and clusters, so too are the moments of life bound together in patterns often unseen. A galaxy may seem like a solitary island until the web reveals its connections, just as an individual may feel alone until they glimpse the wider network of relationships and histories they are part of. Collisions, whether between galaxies or ideas, are not random. They are points of contact that can lead to growth, transformation, and new forms of beauty. In the cosmic web, there is no true isolation, only varying degrees of connection. Galaxies pull on one another across millions of light years, responding to gravity's quiet tug. Clusters form where filaments intersect, like knots tying together a cosmic net, and within those knots galaxies collide, merge, and settle into new shapes, all while the larger pattern endures. The web is both fragile and eternal, delicate in its lace-like structure, yet robust across billions of years. To step back and imagine this web stretching across the observable universe is to embrace a perspective both calming and profound. Collisions lose their violence when seen as part of this grander choreography, just as waves on the ocean are not disruptions but expressions of the sea itself. Galaxies do not simply smash into one another. They are drawn along the filaments of the web, guided by the very structure that birthed them. In the end, the larger cosmic web teaches a lesson of interconnectedness. Galaxies may burn brightly, fade, or collide in dazzling displays, but none of these stories exist in isolation. They're all chapters in the grand book written by the universe itself, a book where every galaxy is both author and character, where every collision is a paragraph in a story that spans billions of years. The web ensures that nothing is wasted, that every encounter contributes to the ongoing evolution of the cosmos. It is a vision of the universe that is at once scientific and deeply calming, a vast, interwoven structure where even the most tumultuous collisions are part of a greater harmony. The galaxies, strung like pearls along filaments of dark matter, remind us that connection lies at the heart of existence. And as we look up at the night sky, the stars are not scattered randomly, but glowing signposts of a web that binds us all into the same cosmic story. In the grand theatre of the cosmos, galaxies are not only graceful dancers in colossal collisions, but also opportunistic feeders. While spectacular mergers between giants like the Milky Way and Andromeda capture most of the headlines, a quieter and more common story plays out in the background: galactic cannibalism. This is when a large galaxy slowly consumes a smaller one, pulling it apart star by star, gas cloud by gas cloud, until little remains but faint streams of stellar debris. In other words, it is cosmic snacking on an interstellar scale. The universe is full of dwarf galaxies, small, faint collections of stars, gas, and dark matter that are often thousands of times less massive than their bigger cousins. They orbit larger galaxies like bees around a hive, bound by gravity but fragile in comparison. To a giant spiral like the Milky Way, a dwarf galaxy is less a rival and more of a light appetizer. Gravity does the work, stretching and tearing until the smaller companion is absorbed into the larger system. Far from being rare, this process has shaped nearly every large galaxy in the universe. Our own Milky Way is a prime example of a cosmic predator. Look closely at its halo, the vast faint outer region of the galaxy, and you will find ghostly trails of stars that do not belong to its spiral arms. These are tidal streams, the remains of smaller galaxies that have already been digested. They are silent reminders that our galaxy's growth has come not only through peaceful star formation, but also through a long history of consuming its neighbours. One of the most striking ongoing meals is the slow destruction of the Sagittarius dwarf spheroidal galaxy. Discovered in the 1990s, this small galaxy is currently being pulled apart by the Milky Way's gravity. The Sagittarius dwarf once circled our galaxy like a loyal companion, but over time its orbit has decayed, and now it is stretched into a long ribbon of stars that wrap around the Milky Way like a tattered scarf. Each pass through the Milky Way's disk tears away more material, leaving behind glittering streams that arc across the sky. Eventually Sagittarius will be fully consumed, its stars settling into the larger family of the Milky Way as though they had always been there. This process is not violent in the sense of crashing stars or exploding systems. For the individual stars within a dwarf galaxy, the experience is often uneventful. Stars are so small compared to the vast emptiness between them that they rarely collide. Instead, the dwarf galaxy's stars simply find themselves tugged into new orbits, carried along by the gravitational tide until they are spread thinly across space. To an observer inside one of those stars' solar systems, the sky would slowly change over billions of years, constellations distorting and drifting as the galaxy around them is dismantled. The Sagittarius dwarf is not alone in meeting this fate. The Milky Way has a collection of smaller satellites, including the Magellanic Clouds in the southern sky. These two irregular galaxies are currently engaged in their own gravitational dance with our galaxy. While the large Magellanic Cloud is still relatively intact and robust, simulations suggest that in the far future it too may be drawn fully into the Milky Way, becoming part of its stellar population. For now, it supplies streams of gas known as the Magellanic Stream, a trail of material pulled away by our galaxy's gravity. On a larger scale, this kind of cannibalism has shaped galaxies across cosmic history. Observations of giant elliptical galaxies, the vast smooth systems often found at the centres of clusters, reveal that they have grown by swallowing countless smaller galaxies. Their halos are littered with faint tidal streams, signatures of their gluttonous pasts. These giant ellipticals are like the heavyweight champions of galactic dining, their immense size a result of billions of years spent absorbing their neighbours. One particularly vivid example is the Andromeda Galaxy, our nearest large neighbour. Studies of its halo show a patchwork of stellar streams, the remnants of past meals. In fact, Andromeda is thought to have consumed several large dwarf galaxies over its lifetime, giving it a complex history of mergers and cannibalism. When Andromeda eventually merges with the Milky Way, it will bring this appetite with it, and together the two will have a shared history of countless absorbed companions. Why does galactic cannibalism happen at all? The answer lies in the simple pull of gravity. Large galaxies sit within massive halos of dark matter, invisible but dominant in shaping their structure. These halos extend far beyond the visible stars, creating an immense gravitational well. Smaller galaxies that wander too close find themselves trapped, their orbits decaying slowly as they lose energy through gravitational interactions. Over billions of years they spiral inward, stretching and breaking apart until they dissolve completely. For astronomers, these cannibalistic events are not just curiosities, but vital clues to galactic evolution. By studying the tidal streams of stars left behind, scientists can reconstruct the history of mergers that built a galaxy. It is a bit like archaeological work, except instead of pottery shards, the evidence is entire populations of stars tracing arcs across the sky. These stellar fossils allow researchers to map the invisible dark matter halos that guide the process, offering insights into the hidden framework of the universe. Despite its ominous name, galactic cannibalism is not necessarily destructive. It is one of the main ways galaxies grow and diversify. The Milky Way itself would not look the way it does without a steady diet of dwarf galaxies. The stars consumed from these smaller systems add to its halo, enrich its chemical composition, and seed its outer reaches with variety. Even our Sun may owe some of its ingredients to past galactic snacks, since the heavy elements that make life possible often come from stars born in galaxies that were later devoured. The term cannibalism also hides the elegance of the process. There are no fiery explosions or monstrous chomping jaws. Instead, there is patience. Over hundreds of millions of years, gravity gently dismantles a smaller galaxy, stretching it into luminous threads that slowly blend into the larger whole. It is more like watching mist being pulled apart by the wind than a violent act of consumption, and in this way the universe demonstrates that even destruction can carry beauty, leaving behind rivers of stars that trace graceful arcs across the night. Humour too has its place in this cosmic dining table. If the universe were a restaurant, dwarf galaxies would be the appetizers, while major collisions like the Milky Way and Andromeda would be the main courses. The Sagittarius dwarf is currently being nibbled away, an ongoing snack for our galaxy that has lasted billions of years. And when Andromeda arrives, it will be a feast to end all feasts, reshaping both galaxies into something entirely new. Galaxies, it seems, are not just dancers but gourmets, forever dining on one another in the quiet dark. What emerges from this cosmic dining habit is not waste, but transformation. Smaller galaxies may vanish, but their stars live on, integrated into the fabric of larger systems. Cannibalism in this sense is less about loss and more about rebirth, with each galaxy that disappears helping to shape the grandeur of those that remain. It is a cycle that has repeated since the earliest epochs of the universe, and will continue for as long as galaxies exist. Seen in this light, galactic cannibalism is less a tale of destruction and more a reminder of the interconnectedness of cosmic life. The stars of a devoured dwarf do not vanish. They join the vast chorus of light in the larger galaxy, shining just as brightly, only in a new arrangement. In the end, what seems like a cosmic snack is really a quiet act of creation, the universe folding small stories into its larger narrative. The universe has always been a restless place, never content to let galaxies sit quietly in their corners of the cosmos. Gravity, the great matchmaker, ensures that galaxies drift toward one another, slowly entwining in dances that last billions of years. For now, these mergers are scattered and dramatic events, each a highlight in the history of a particular system. But when you stretch the clock forward into the deep future, galactic collisions become more than isolated spectacles. They become the dominant story of the universe itself. Our own Milky Way is already fated for such a future. Its collision with the Andromeda Galaxy will create a new hybrid system, sometimes jokingly called Milkdromeda. That event will not be the end of the story, though, far from it. Once Milkdromeda settles into its final elliptical form, it will keep pulling in smaller galaxies from the local group. The Triangulum Galaxy, the third largest member of our neighbourhood, may be swept in as well, ensuring that the local group eventually becomes a single massive elliptical galaxy surrounded by faint debris streams. What is today a family of galaxies scattered across several million light-years will condense into one luminous heavyweight. This process is not unique to us. All across the cosmos, galaxy groups and clusters are heading towards similar outcomes. Smaller galaxies are steadily being consumed by larger ones, and clusters themselves are tightening as their members interact and merge. On cosmic scales, collisions are less about chaos and more about consolidation. Galaxies are gathering together, forming fewer but larger systems. It is a kind of slow cosmic convergence, gravity patiently gathering its flock. The reason this happens is simple. Dark matter halos, those invisible cocoons of gravity that surround galaxies, stretch across immense distances. When halos overlap, galaxies become bound to one another, eventually spiraling inward over billions of years. Left unchecked, this means the future universe will be dominated by enormous elliptical galaxies, each one the result of countless mergers and meals. The universe may not always look like the spiral-rich cosmos we see today. Instead, its far future may be a landscape of smooth, rounded giants, glowing quietly but lacking the delicate arms of spirals. As the universe ages, these mergers will become fewer but more impactful. Right now, galaxies are relatively close together compared to their size, making collisions common over billions of years. But cosmic expansion complicates things. Space itself is stretching, driven by what is called dark energy, and distant galaxies are being carried farther and farther away. Over vast timescales, only galaxies gravitationally bound together, like those in our local group, will remain accessible. Everything else will slip beyond the cosmic horizon, receding faster than the speed of light due to expansion. In this sense, Milkdromeda and its future mergers represent a rare last act. Beyond our local neighbourhood, the rest of the universe's galaxies are destined to disappear from view entirely. Imagine the night sky of a civilization living trillions of years in the future, long after the Milky Way and Andromeda have become one. To them, the universe may seem much emptier than it does today. They would look up and see only their own colossal galaxy dominating the cosmos. The countless galaxies we see with telescopes now, spirals, dwarfs, irregulars, will have slipped beyond reach. The universe will appear strangely insular, as though their galaxy were the only one that ever existed. This is not because the galaxies are gone, but because the expansion of space has carried them away into unreachable darkness. This paints the future of galactic collisions as both spectacular and melancholy. On one hand, the merging of galaxies like the Milky Way and Andromeda is a grand finale, a fireworks show written in starlight. On the other, it is also a closing of the curtains, as the broader cosmic stage fades away, leaving each bound cluster or group isolated in a darkened universe. The age of galactic collisions will eventually give way to an age of cosmic solitude. Within these isolated future galaxies, stars will continue their own cycles of birth and death. For a long while, mergers will fuel bursts of star formation as gas clouds collide and compress. Quasars and brilliant starbursts will blaze, making some galaxies brighter than ever before. But gas is a finite resource. As it is consumed by starbirth or ejected by black holes, galaxies will run out of fuel, star formation will slow and eventually stop. The great elliptical galaxies left behind by collisions will gradually age into quiet collections of long-lived stars. Over trillions of years, the glow of galaxies will dim further still. The most massive stars will have long since died, leaving behind only red dwarfs, which can burn for trillions of years. These faint ember-like stars will give galaxies a soft reddish hue, far dimmer than the vibrant spirals of today. Even galactic collisions at this stage will lack the fireworks of earlier epochs, as there will be little gas left to spark new stellar generations. Instead, mergers will simply mix populations of aging stars, folding one quiet galaxy into another, and then, farther ahead than the human mind can easily grasp, even those red dwarfs will fade. Galaxies will become collections of stellar remnants, white dwarfs, neutron stars and black holes, drifting silently through the dark. Collisions may still happen, but they will be muted affairs, bringing together remnants rather than sparking life. Eventually, even black holes themselves may evaporate through a process known as Hawking radiation, leaving behind only faint whispers of energy in an otherwise empty cosmos. In this vision, galactic collisions are not just a chapter in cosmic history, but also a pathway toward the universe's ultimate destiny. They build the great galaxies of the future, even as they preside over the gradual fading of starlight. Each collision is both creative and destructive, a moment of brilliance that ultimately contributes to the stillness to come. It is sobering, but also strangely calming to imagine this progression. The universe is not rushing to its end in a sudden catastrophe. Instead, it is gently dimming, one collision, one star, one galaxy at a time. Billions of years into the darkness, the great cosmic mergers will be among the last acts of grandeur before silence takes over. Even then, the legacy of these collisions will remain in the shapes of the galaxies they built, the stars they birthed, and the black holes they fed. From the perspective of the present, collisions seem like wild, dramatic spectacles. Galaxies slamming together, starbirth igniting, black holes roaring. But from the perspective of eternity, they are simply part of the universe's slow transformation from youth to maturity to quiet old age. Galaxies are not only dancers and diners, but also builders, their collisions shaping the very architecture of the cosmos for as long as it has time left. So the story of galactic collisions does not end with Milkdromeda. It stretches across billions and trillions of years, echoing into a future where the universe grows dark but not meaningless. Even in the fading light, the quiet forms of merged galaxies will drift through the expanding void, carrying within them the history of all the collisions that made them. In this way, collisions are not only a spectacle of the present, but also a bridge to the farthest future, binding together the universe's past, present, and final whispers of existence. Galactic collisions matter because they are not accidents or curiosities of the universe, but essential architects of its very shape. The cosmos as we know it would not exist without these gravitational encounters. The spirals, ellipticals, starbursts, and even the vast clusters of galaxies strung together like pearls on filaments all owe much of their existence to collisions. To watch two galaxies merge is to witness cosmic evolution in its most visible form, a transformation that builds structure from chaos. When two galaxies approach, their invisible halos of dark matter tug at each other long before the stars and gas clouds begin to mingle. This gravitational handshake sets the stage for what follows. The galaxies stretch, distort, and often fling out long tidal tails, bridges of stars and dust that trace the invisible threads of gravity in space. These encounters can trigger starbursts, fueling new generations of suns that otherwise might never have formed. Without collisions, the universe might be far less rich in stars, planets, and potentially even life itself. Collisions also provide answers to some of the universe's deepest puzzles. By studying them, astronomers learn how galaxies evolve from delicate spirals into smooth ellipticals, why some systems blaze with quasars, while others fade into quiet dimness, and how dark matter shapes the visible. Each merger is a natural experiment played out on scales so vast that only patient starlight and cosmic time can reveal the outcome. Beyond the science, collisions remind us that the universe creates beauty even in its most violent acts. Photographs from space telescopes reveal galaxies locked in embrace, their arms twisted into shimmering arcs, their cores glowing as they funnel matter into central black holes. These images look less like destruction and more like art. Paintings drawn with light and gravity across the backdrop of eternity. Each collision becomes a masterpiece, unique in form, yet part of a universal theme. It's hard not to reflect on what these galactic encounters say about cycles of change. Collisions seem catastrophic, yet they are builders more than destroyers. Stars themselves rarely collide, given the vast distances between them, so most survive the encounter unscathed. Instead of annihilation, mergers often bring renewal. Fresh bursts of starlight, galaxies reborn into new shapes, and central black holes give new fuel to shine. Even the apparent chaos serves a greater order, weaving galaxies into ever larger structures that echo across billions of years. In this way, collisions are lessons in endurance. A galaxy can be torn apart, stretched thin, or folded into something entirely new, yet it remains. Its stars carry on their slow journeys around whatever new core gravity fashions. Its gas clouds find fresh balance, condensing again into nurseries of light. Out of collision comes continuation. The universe itself is showing that change, even dramatic upheaval, is not the end of the story but part of the rhythm of existence. One of the most profound aspects of galactic collisions is their scale of patience. These dances last hundreds of millions, even billions of years. What looks like a violent clash is in reality a slow unfolding, as deliberate as a symphony played across cosmic time. From our perspective, we capture only brief snapshots, a tidal tale here, a starburst there. To the universe, though, it is all one long, graceful movement, galaxies weaving together in silence. This patience makes collisions comforting to contemplate. They remind us that even events that appear catastrophic when viewed in isolation are, in the broader span of time, simply part of a larger harmony. Galaxies endure through transformation, and so does the universe itself. Far from random destruction, collisions illustrate how order and beauty emerge from change. There is also humility in realizing that our own galaxy is not exempt. The Milky Way, with its billions of stars and its home to countless worlds, is destined to merge with Andromeda. To imagine such a future is not to fear it, but to recognize that we belong to a universe of cycles. The Milky Way will not end. It will become something larger, part of a story that extends beyond its current shape. Just as individual stars pass through stages of birth and death, galaxies too pass through phases, with collisions as their transformations. These encounters also highlight the interconnectedness of the cosmos. No galaxy is truly isolated. They are all part of a larger fabric, woven together by gravity into clusters, filaments, and superclusters. Collisions are the threads pulling that fabric tighter, ensuring that no part of the universe evolves alone. When we look at colliding galaxies billions of light years away, we are not witnessing something foreign, but glimpsing the same process that shapes our own cosmic neighbourhood. The beauty of galactic collisions is not only in their luminous arcs and glowing centres, but in what they reveal about resilience. They show us that change, however dramatic, carries seeds of creation. They show that the universe, for all its violence, is also a patient gardener, pruning, reshaping and nurturing new growth. And they remind us that even when structures dissolve, their essence continues in new forms. On the human scale, collisions are far too slow to fear. But as metaphors, they speak deeply. They show that endings are rarely final, that upheavals are often preludes to new patterns, and that endurance often means accepting transformation. Galaxies teach this silently, drifting through their collisions with grace that only becomes clear when viewed across the span of eons. Ultimately, galactic collisions matter because they are the universe's way of sculpting itself. They give shape to galaxies, fuel the birth of stars, and reveal the hidden framework of dark matter. They matter because they are breathtakingly beautiful, natural art written in starlight. And they matter because they reflect truths larger than science, that change is constant, that cycles are inevitable, and that endurance often comes through transformation, not resistance. To contemplate galactic collisions is to glimpse both the grandeur of the cosmos and the quiet wisdom it carries. In their luminous arcs and swirling forms, galaxies whisper that even in upheaval there is beauty, and even in endings there are beginnings. Their story is one of resilience and renewal, written across billions of years, a reminder that the universe, like life itself, thrives not in spite of change, but because of it. Galaxies collide, but not in the way one might imagine. There are no deafening crashes or blinding explosions, only a slow unfolding of gravity's patient choreography. These encounters stretch across hundreds of millions, even billions of years, moving at a pace so gentle that if one could watch in real time, it would seem as still and calm as the turning of seasons. What from afar looks like violence is in truth a graceful inevitability, a reshaping rather than a ruin. And while it is true that our own Milky Way is destined to merge with Andromeda, this is not a cause for worry. The timescales are vast beyond comprehension. It will not happen tomorrow, not in 1,000 years, not even in 1,000,000. Billions of years lie between the present moment and that distant meeting, far longer than the sun itself will remain in its current form. There is no need to cancel weekend plans, or even to think of it with fear. By the time such an event unfolds, our place in the cosmos may have shifted entirely. What matters instead is what these collisions reveal. In their arcs of light and rivers of stars, they show that the universe is not chaotic, but deeply ordered. Even in upheaval, there is balance. Even in endings, there are beginnings. Galaxies may twist, stretch, and merge, but they endure, becoming new forms, new homes for stars, new patterns of beauty etched across the sky. The thought can be oddly reassuring. If galaxies themselves survive the pull and push of such cosmic encounters, then perhaps endurance is written into the very fabric of existence. Change, no matter how sweeping, is not destruction but transformation, and in the long silence of space, where galaxies drift together over eons, the universe reminds us that time softens all turbulence. So, as the story of colliding galaxies winds down, rest in the knowledge that the cosmos moves with patience, not haste. That what may appear as chaos is, in truth, creation at work, and that even across billions of years, beauty endures, quietly, gracefully, unshaken by the dance of gravity.